Good evening, all of you. So is audio video clear for all? Yes, by maybe by mistake that signals and system is added. Now you can check now it is changed. It was updated now. Transformer day 2 will be there. Okay. Okay, right. In the last class we started construction of transformer. Mainly we have two parts now. One is transformer core and transformer winding. So we started first one transformer core, and in that we have seen some concepts like we preferred silicon steel because of some important properties it is having, like high permeability, low reluctance, ferromagnetic material. These are all. And still we go with CRGO steel because in silicon steel we have a small problem. That is, silicon steel is a non-oriented steel. So in order to make that orientation, we are doing cold rolling process on that. So it will become CRGO steel. Okay, that is also silicon steel, but oriented steel it is. Silicon steel is two types: non-oriented steel, oriented steel. Non-oriented generally we use in all rotating machines like DC machines, synchronous, induction, everywhere. But only in transformer we use a CRGO steel, that is oriented steel. Due to that, the reluctance is reduced by little, so that flux magnitude increase, power transfer capability also increases. And we are using laminated core, but not solid core, because if we use solid core now, main problem is eddy currents, which causes eddy current loss, and due to that heat is producing. And whenever heat is increasing, what is the problem for any machine? If heat increase, heat is very important to be reduced. That may be transformer or that may be rotating machines, anywhere. Otherwise, if heat is increasing, and if heat continuously increase like that, the first thing damage is copper winding. Copper winding will melt at high temperatures, so that should be reduced, so that cooling should provided. For that we are using transformer oil, or we can use like breather is one of the method which provides cooling to that breather. And also we are using fans at the bottom of transformers or side by, we are using fans to take that heat continuously outside. Okay. And we have seen two types of cross section. We have cross section of the core where we place winding. What are the two types? One is square core and other is stepped core. We prefer little stepped core, not so many steps, because if steps is like 4 or 5 steps now, then advantage is there, but main problem is what? Again, construction problem. Many different sizes of laminations we have to design, so that is difficult. That's why 2 3 steps mostly we preferred in order to reduce diameter, so that insulation required reduce, copper requirement also reduces. Stepped core we are using. Okay. Now after that we have seen about difference between transformer and induction motor briefly. Now let's see some small numerical. Then we go to types of magnetic circuit. With the types of magnetic circuit, the first part will complete. Transformer core will complete. And then we go to transformer winding, second one. Okay. See here. See this question. Read the question. A 400 by 200 by 200 volt, 50 hertz, 3 winding transformer is connected as shown in figure. The reading of voltmeter. So generally the figure looks like a little complex. Actually, if you redraw the figure, it is very simple diagram, so that easily you can understand. This is the figure. So three windings are connected like this. Polarities are very important here. You should not change by mistake that polarities. 400 volts, 50 hertz, and 400 is to 200 is to 200. So these are number of turns in each winding. Okay, 400 turns. Now you can easily identify 400 turns it is. This is 200 turns. This is 200 turns. All are on the same core. All three windings are on same core. So what is the EMF per turn or voltage per turn for every winding? Same. So where source is connected? 400 turns source is connected. Polarity is important. Mark properly. Here dot. Then dot is connected with the dot. Now undot this is and connected with the dot. This is dot. Okay. This is here voltmeter is placed. Now, this voltmeter reading how much it will read. That is we need to calculate magnitude. Now consider 400 volts is applied to 400 turns. That means what is voltage per turn? 1 volt. Okay, voltage per turn 1. Then 200 turns means what is the voltage reading for this winding here? 200 volts. This is also 200 volts. Why 200? According to given source, 400 volts is applied to 400 turns. Then what is voltage per turn? 1 volt. 400 turns, 400 volts. Like the 200 turns, 200 volts, 200 turns, 200 volts. Now, how much this voltmeter will read totally in this loop here? Now, observe, you can consider dot means plus or minus, anything you can take, but follow one. So, I'm following dot is plus, plus, this is plus, minus, minus, here minus. Now, if you observe, these two are connected in additive, no? Observe these two windings, plus is connected with minus here. Plus is connected with minus, so 400 volts. Additive it is. Same polarities when you connect, that is subtractive. Opposite polarities, additive. So 200 plus 200, 400. Now overall it is 400. Here plus, here minus. Now if you check with respect to this first winding, here plus is there. Now this is also plus. Plus plus connected means subtractive. Then 400 minus 400. The voltmeter reading is finally 400 minus 400. This is equal to 0 volts. Okay. The voltmeter reading will be 0. Yes, 0. But the dot polarity important. So here they given directly in the diagram itself the dot polarities. Based on that you need to answer voltage. This line indicates what here? Transformer core it is. The two lines between the winding is what? Core. Otherwise, if it is not there, no, that is maybe air core. If it is not indicated, the two lines indicates that it is a air core. Okay, completed all of you. No, in this diagram we cannot find dot. If it is not given dots, no, we cannot find that because here there is no core indicate. That is actual previously we taken transformer core and winding their flux directions we are drawing. But how can we draw flux direction all in here? For that reason, so they should give dots here. Otherwise, we cannot solve. Here phase angle is not given. First of all, the reference is not given. What it is 0 or 60 degrees or what it is not given. So we don't consider angles here. Direct magnitudes we are taking. Okay. Next question. See this question. See the question. Yes, when you connect same polarity, subtractive. Opposite polarity, additive. When there is dot polarity in the question, you no need to apply any current direction, any flux direction. Directly, you can apply this additive or subtractive, what it is. That's it. No need of current entering or leaving here, because directly given dot, according to their given dot notation, we need to find. Okay. And observe this question. This is little confusion will come because in the question itself, they given little wrong. So maybe it is wantedly given or given directly it is, but according to the question, you need to answer properly. First, read the question. The core of a two-winding transformer is subjected to a magnetic flux variation as indicated in the figure. So flux waveform given. Flux waveform given. The induced EMF ERS. This is secondary side. Secondary winding as a function of time will be of the form. Induced EMF we need to find from the given flux signal. What is the formula? Secondary side EMF E2 equal to actually I said previously it is minus n into d phi by dt. So when we have to put minus, when we should not put minus, that is also I said yesterday. If in the question, if they given dot polarity, you should not take minus here. Okay. If they given dot polarity, you should not take again minus in the equation. If it is not given in the question, that is in the diagram, if dot is not given, then only you have to take minus here. So minus indicates what? According to Lenz law, we are placing that. That's it. So once you applied dot here, means Lenz law is considered. So you should not put again in the EMF equation. Okay, as they given already, you don't take here. So you directly calculate ERS. ERS equal to n into magnitude, directly I'm calculating n into d phi by dt. So number of turns is given, secondary side. What is the number of turns on secondary? 200. And flux signal or variation is given with respect to time. So that slope you have to find for each case, 0 to 1 second and 1 to 2 second and 2 to 2.5 second. So individually calculate. First, 0 to 1 second. Calculate ERS. 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 N 200 into change in flux with respect to time. 0 to 1 second. Time is what? 1 second only. And how much flux is changing? Initially at 0, flux is 0. Now at 1, t equal to 1 second, what is the magnitude of flux? 0.12 Webers. So how much change? 0 to 0.12, like the slope y2 minus y1 by x2 minus x1. Okay, slope y2 minus y1 by x2 minus x1. You can consider x1 y1, and this point is x2 y2. X1 means 0, y1 also 0, 0, 0, comma 0. And x2 y2 is what? X2 means this y axis, t axis, time. So this is 1 second, and comma y2 means y axis variation, that is flux 0.12. So apply that y2 minus y1 by x2 minus x1 if you have confusion. How much it is? 0.12 minus 0 divided by 1 second minus 0. So how much it is? 24. 24. This is ERS. ERS. Okay. In the same way, you calculate 0 to 1 second we calculated, and now 1 to 2 second. 1 to 2 second. In this duration, calculate what is the magnitude of EMF, ERS. Same formula, 200 into d phi by dt. What is the flux in both cases? At 2 points, same flux, no? What is the change in flux? No change in flux. So flux change is 0. Divided by, what is the time change? 1 second to 2 second is difference, 1 second only. So anyhow, as it is 0 flux variation, this is 0 volts. This is 24 volts. Next, 2 to 2.5 second. So in this duration, what is ERS? Calculate n into d phi by dt. Now 2 to 2.5. Initially flux here 0.12, and what is the flux here? 0. So change 0 y2 minus y1 by x2 minus x1 I'm applying. 0 minus 0.12 divided by time variation 2.5 minus 2, 2.5 minus 2, y2 minus y1 by x2 minus x1. If you have confusion, apply this every time. Calculate what is ERS. How much it is? 2.5, 0.5. This is 1 by 2. 48. 48 volts. Okay. Minus 48 volts. This is minus 0 minus 0.12, no? Minus 48 volts. So which option will come? There is a little important observation. So let's find what is your answer. Which option is right? Okay, yes, wait here. So most of you saying option A. Most of you saying option A, but that is wrong, because in the question itself they given wrong polarity. Check it is. So according to you, primary side it is given dot here, P is dotted terminal. Secondary side you try to mark where is the dot polarity will come. You try to mark where is the dot, at R or at S. They given at R. Is it right or wrong? Check is it right or wrong. Yes, that is wrong. The given dot is at R. This is wrong. Why? You apply the dot convention. See, flux direction they given, main flux it is. Current is entering here. So this is the direction of current in the winding. So flux will flow in the clockwise direction. This is main flux. Okay. Main flux is flowing in this direction, clockwise, by applying right hand thumb rule. Main flux it is. Now what should be the flux due to secondary winding? Opposite. Opposite. Take opposite. Upward direction. Upward. Now apply right hand thumb rule. Upward direction is flux and 4 fingers is current. Then if you apply, so I'm getting current is like this. Current is like this. And here it will go inside and comes outside directly. Now, according to dot convention, what is the statement? If current enters at dot on primary, current should leave at a dot on secondary. So where should be the dot exactly? Dot should be at S. This is right. But they given dot is at R, that is wrong. Okay. So dot should be at S. If it is ESR, you are calculating, no? Whatever you calculated, they are correct. Whatever you calculated, they are correct only. But what they asked to find, ERS they asked to find. If it is ESR, these values are correct. But they are asking ERS. That's why whatever you are getting, you should take for this negative. Take negative. 24 volts you got, no? Means minus 24 it is, because dot they given wrong here. Dot they given wrong. That's why you need to change the polarities for your EMF. Minus 24, 0, minus 48 will become plus 48. So what is the final answer? Minus 24, option B. Minus 24, 0, minus 48 will become plus 48. Okay. Clear all of you? First, we need to check whether they given correct polarity or not first. Then we need to proceed. So directly we proceed here first. And then we come to know the polarity given in the question itself wrong. That's why we changed our values in this. Just we take and reverse. Positive value negative, negative value positive. That option B is correct. Actually, question itself it is wrong, because the dot convention is wrong. Secondary side dot must be at yes. Okay, dot must be at yes. And they are asking ERS. if they asked find ESR, then whatever the values you calculated, that they are correct. But they are asking ERS, R to S they are asking. That's why we are changing polarity. Okay. Yes, if dot is at yes, that is positive. Yes, definitely. Okay. Let's see now. In the transformer core, first part, the next topic is one second. Okay, right. Right. The next topic is types of magnetic circuits. So this is also under transformer core only. Types of magnetic circuits. So among all, this is important little for the questions like conventional questions in either junior engineers or engineering services. This question is important. This topic, types of magnetic circuits. So previously also we got many times explain the types of magnetic circuits of single phase transformer. So however, we have here types of magnetic circuit in single phase transformer. In the same way, in three phase transformer also we have. Okay. So once we start three phase transformer, again we will see the same topic, types of three phase magnetic circuits. Two types we have, like in single phase. So we have two types. One is called core type transformer, core type magnetic circuit. And second, shell type magnetic circuit. Core type and shell type. Two types we have. So take the figures. So while drawing figure, take care little. So don't draw blindly these diagrams. So however, I'm drawing almost draw like this one because in core type, if you observe, What is the vertical section of this core? We call limb. Vertical we call limbs. We have two limbs here. See, this is limb, and horizontal part of this core we call yoke. So this is vertical part, limb we call. And here also these are the limbs. Three limbs we have here. Three limbs. In shell type, three limbs. In core type, two limbs. And the two limbs should have same cross sectional area. Two limbs are having same area here. Observe, if it is having area A, it is also having same cross sectional area. But in shell type it will change. You should change this. Not same, it is only at the center. If it is area A, suppose the middle limb is area A and outer limbs must be half of this. Like this we design shell type core. The outer limbs must be half of that middle limb. Okay, now draw the figure completely. So tell me one question. In your labs, maybe mostly all of you, maybe those who are in second year, you may not did, and mostly from third year, so you have did OC test and SC test on transformer. Test on transformer in the labs. On which type of transformer you did the test? Core type transformer or shell type transformer? Tell me this. On which type of transformer you did test, that OC test and AC test? Core type or shell type? Because most of the people will not observe all of this. Directly they will do the test. Okay, most of you saying core. Most of you saying core, but the answer is shell. So if you remember, no, in your lab, that on the table, when you place that single phase small transformer, core will be there, no, outside. Winding will be inside. Core will be outside. Core will look outside first. So they are all shell type transformer. So simply you can remember also. Mostly all types of low voltage rating transformers belongs to shell type. Not only there, in your home also, if you have amplifiers or televisions, old televisions, so mostly you will have one small transformer in that. All the transformers are what? Shell type transformers only. Most of the domestic purpose transformers belongs to shell type, because for low voltage they are suitable, and shell type is best for low voltage application, and core type we use for high voltage application. Okay, now observe some differences between these two, core type and shell type transformer. In core type, where we have the windings are located. First of all, this core type having two limbs having same cross section area, and shell type is having three limbs having area such that the middle limb area is A and outer limbs area is half of the middle limb. Okay, so write the first point. It is having two limbs. It is having two limbs. Two limbs of same cross sectional area. So you write that point. It is having two limbs of same cross sectional area. Same cross sectional area. Next, in shell type, it is having three limbs. It is having three limbs such that it is having three limbs. Continue that. Such that the area of outer limbs is half of middle limb. The area of outer limbs is half of middle limb. Yes. A means area of cross section. Next point. Now observe, in core, the windings are on separate limbs. So one winding is on one limb, other winding is on other limb. But in shell type, where we have the two windings, the two windings are located on the same limb, that is the central limb or middle limb. So write that point. Second point. Second point. The windings are placed on separate limbs. The windings are placed on separate limbs. Separate limbs. In shell type, the windings are placed on same limb. The windings are placed on same limb. Okay, the windings are placed on same limb. Next point. Observe the figures. Out of these two transformers, two circuits, two magnetic circuits, in which case the winding is well protected, core or shell? The winding having well protection in core type or shell type? Definitely shell type. Well protection for winding in shell type, because where winding here inside, outside what we have? Core we have. So core is a strong body, no? That's why it is well protected by the core, because winding is inside. So right in core type, the winding is not protected well. The winding is not protected well. Next, in shell type, the winding is well protected. The winding is well protected. Okay, next point. The winding is well protected in shell type transformer. Now, if you observe, when we give supply, now let us give supply to one of the winding, primary side here. So when we give supply to transformer, current is flowing. Now due to that current, a flux will produce, and same flux directly goes to secondary side. Okay, this is the path of flux. In the same way, out of the two windings, give supply to any one winding. Suppose I am giving supply to this winding, then current will flow here and flux will produce. Now whatever the flux produced here, whatever the flux produced, this flux, out of the total flux, half of the flux will go in this direction, and remaining half of the flux will go in other direction. So whatever flux produced, total flux phi, whatever the flux produced, it is going to secondary side, secondary winding, no doubt. But how it is going? It is first divided into two paths. Half of the flux in one direction, other half in other direction, and then it is coming to secondary side. So out of these two, which looks like a series circuit and which looks like a parallel circuit? Definitely core type is looks like series magnetic circuit, because whatever flux produced directly it is going to secondary, series it is. But in shell, the flux is first divided into two equal paths, two equal halves, and then again combined at secondary. So this is called parallel magnetic circuit. Shell type is called parallel magnetic circuit. Core type is called series magnetic circuit. So write that point. It is a series magnetic circuit. It is a series magnetic circuit. Next, in shell, it is a parallel magnetic circuit. It is a parallel magnetic circuit. Okay, next difference. Now observe, every transformer practically will have some leakage flux. Every transformer will have some leakage flux. Now which transformer will have more leakage flux? So first of all, we should know what is leakage flux. Now observe here, what is leakage flux? Observe this. So whenever we give supply to any one of the winding, primary side, suppose current is flowing, flux is produced. Now whatever the flux produced on primary is total flux will reach to secondary. Suppose 100 flux lines produced primary side, all 100 flux lines will go to secondary. No, practically it won't go. Out of 100 flux lines, maybe one line or two lines or three lines will be leakage, means that lines will not reach secondary. Now where they will go? Now they will go in the air itself. So here a small amount of flux will be leakage here. Some small amount of flux, two three lines, suppose for example, these flux lines we call leakage. So what is leakage flux definition now? This is one of the gate question also. Leakage flux, but it is given for induction motor or transformer, anything, same definition. So what is leakage flux? The flux which links with only one winding, but not both windings. Now observe, whatever flux going in the core, this is linking with both windings. Then is it a leakage flux? No. This is called main flux, or also called useful flux. This is called useful flux. But some flux is what happened? Leakage. Here itself it is rotating through air itself. That is called leakage flux. So leakage flux will be there on primary and it will also there on secondary. But as it is open, no secondary side here, is there any current in secondary winding? If it is open, no currents. So when currents will flow on secondary? Only when you connect load here, then only currents will flow. So whenever there is a current here, let's secondary current I2, now it will produce some more flux here. So clearly you will see that is in operation. So why I'm saying is, don't say that leakage flux is only on primary side. Okay, leakage flux will be there on primary and also on secondary when load is connected. Both sides it will be there. So anyhow, now what is leakage flux here? More or less. Now let us see for shell type similarly. When you give supply to this winding, primary winding, current is flowing and flux is produced. In that, a small amount of flux is leakage. Okay, small amount of flux leakage. Now tell in which type of magnetic circuit we have more leakage flux. Definitely core type. Why in core type? Because what is the distance between these two windings? More here, more distance. But in shell type, what is the distance between these two windings? Very less, because both are on the same limb. So what happens here is, some flux is going in the air, actually it is leakage, but what happens is there is a chance that that flux directly enters into secondary winding through air itself. Now is the flux leakage? No, this is not leakage. Flux is going to secondary now, but it is going by air but not core. There will be leakage flux. Suppose I said here three lines is leakage in core type. In shell type, maybe one line is leakage. One line is rotating here itself. It is not coming to secondary side. Okay, so leakage flux is less for shell type transformer and leakage flux is more in core type transformer. Okay, first write the definition of leakage flux. Right, definition: leakage flux. This statement is same for induction motor also, but there we call stator winding, rotor winding, and here we call primary winding, secondary winding. Write the statement: the flux which links with only one winding, which links with only one winding, only one winding, but not both windings, but not both windings, is called leakage flux. Is called leakage flux. If in case of induction motor, the same statement is the flux which links with the stator or rotor, but not both stator and rotor, is called leakage flux. Okay. Now core type having more leakage flux because more distance between the two windings. Shell type is having less leakage flux. So write the difference. It has more leakage flux. It has more leakage flux. Next, shell type. It has less leakage flux. Less leakage flux. Okay. Next point. Next, observe the figures. Now tell me, by looking at the figures, on which type of core you can place more number of turns, core or shell, more turns, more copper wire, more number of turns, where you can place core type or shell type. Yes, definitely core type. Yes, no doubt, core type, right? Core type we can place. Why we can place? Because there is more space, more distance, or more gap between two windings, more number of turns you can accommodate. But check shell type ones, both are on the same limb, and the width of this window also very less here. So after placing, if you place both windings on same side now, that gap will fill quickly. Then more than that gap you cannot place. So gap available to place turns is less in shell. So we cannot place more amount of turns in shell type transformer. So when you get high voltage, if you have more number of turns in any one winding, you will get high voltage. Okay. So but it is not possible in shell type. That's why shell type is suitable for low voltage purpose only, but core type is suitable for high voltage applications, because more turns is possible to place here, but not in shell type transformers. Right, that point. It is suitable for, it is suitable for high voltage applications. High voltage applications. So remember, in case of three-phase transformer, same topic we discuss there. Then we don't discuss all these points again. Okay, here only we will discuss clearly, but not three-phase again. In three-phase transformer, only one point we discuss. So that is important there, and remaining all same like this only. Next, it is suitable for, it is suitable for low voltage applications. Low voltage applications. Next, now observe these two diagrams. Observe these two diagrams. Here, in each transformer core, we have window. This is called window here. This is inside. This is a window, and this window is having some width. This is the width of the window, and this is height of the window. Okay. One window, single window in core type. But in shell type, how many windows we have? Two windows we have. This is one window, width of the window, and here also one more window. Same width will be there for both. Okay, same. And this is height of the window. So this type, this magnetic circuits we also call like single window transformer, double window transformer. Single window transformer means core type. Double window transformer means shell type transformer. Like this also you should remember. Now, based on the height and width of the windows, we have one important factor. That factor we call window factor. So important. See, window factor. Window factor. WF, window factor. Now this window factor is nothing but, window factor is nothing but, it is the height of window to the width of window. Height of window to the width of window is called window factor. Now what is the importance of this window factor? Yes, this window factor will give the information about leakage flux in transformer. Suppose there are four transformers. they will give different window factor value, 0.9, 0.8, 1.1, 1.2, like this. Then you have to identify which transformer is having more leakage flux, which transformer having less leakage flux, based on the window factors only. Okay, so window factor will give the information about leakage flux in transformer, because they don't tell directly this is core type transformer, this is shell type transformer. They will give window factor value. Based on that value, you need to tell which one having more leakage flux and which one having less leakage flux. Okay, now write this point. It will provide information about will provide information about leakage flux in transformer. Leakage flux in transformer. Leakage flux, and this window factor is inversely proportional to leakage flux. Leakage flux. Now you observe the figures once. Observe the figures. For these two transformers, which variation is more, width or height? Observe height of height for core type transformer, height for shell type transformer. Almost same height only, no? Almost same height. According to diagrams, almost same height they are. But where more variation we are getting? Width. What is the width for shell type transformer? Very, very less when compared to core type. This is the width for core type. So much width is there. More distance between two links. But for shell type, less distance is there. Almost height is same. Now, which one will have more window factor? Window factor is nothing but height by width. Height is almost same, so we are neglecting height variation. But width of core type transformer is more. Whenever width is more, what is the window factor value? Reduce or small. And for shell type, what is window factor? Height is almost same. What is the width of the shell type transformer? Less. As width of window is less, the window factor value is more. Now already you know here which one having more leakage flux. Leakage flux is more in core type. So for core type transformer, what is the value of window factor? Small, less. And for shell type transformer, what is the value of window factor? High. So less window factor indicates more leakage flux, and more window factor indicates less leakage flux, because already we know leakage flux, that is we are placing here. Okay, window factor is inversely proportional to leakage flux. Now write the difference here. Core is having, what is the window factor of core? More or less? Window factor of core is less because more width for this. Write that point. Window factor is less. Window factor is less. And here in shell type, window factor is more. Window factor is more. Based on this window factor, in previous some of the interviews we have question like see that question. Now tell me one question. How can you reduce leakage flux in transformer? How can you reduce leakage flux in transformer with respect to window factor? Tell me. You need to reduce leakage flux. For that, what you have to do? Window factor should be increased. Both are inversely related, no? If you want to reduce leakage flux, you need to increase window factor. How to increase window factor? Window factor is what? Height by width. Height of window by width of window. Now, in order to increase the window factor, two chances we have. One is increase only height of the window, and second is what? Decrease only width of the window. Decrease the width of window. Anyone or both also you can do. So window factor, if you increase the leakage flux in transformer reduce, it is okay because based on the relation you are saying, no doubt. But here the question is how it is. Can you explain practically? So they asked same thing that student also given the reply, by increasing window factor we can reduce leakage flux. But their question is after that, can you explain practically how it is? How can you reduce? Then he cannot because that idea is not there. So how can we practically, how can we explain this phenomenon? Yes, very simple. Now let us consider there is one transformer initially. Core type I am taking, for example, core type. There is some height for this. This is winding. So it is having some height. This is the height of window and this is width of window. Okay. There is some height, there is some width, and there is some leakage flux at that time. Now, if, to reduce the leakage flux, I need to increase window factor by two ways. One is either increasing height of the window or decreasing width of window. Now, first I am going with height of window. I am going with height of window. Already there is some leakage flux here. Let this is the leakage flux in transformer. Previously, small amount of flux is leakage. Now, if you increase height, window factor increase, then leakage flux increase. How it is? See that. Now I am increasing height. First I am increasing height of window. By keeping same width, height of window I am increasing. So height increases, width is almost same. Now how it will reduce? Observe. Whenever height of this window increases, what happens is, this is the path of leakage flux now. So whatever current is flowing here, whatever flux is leakage previously, now it will take this path. This is the path. Now what is the path for leakage flux? Increases or not? Means reluctance increases. No, path increasing means reluctance increasing. Then is the flux will prefer to flow through high reluctance path? No. Whatever there is leakage flux in the previous diagram, suppose 4 lines are leakage previously, but now 4 lines will not be leakage, maybe some 2 or 3 lines will be leakage, not 4, because length increases, reluctance offered to flux increase. So as height increases, the leakage flux in transformer will reduce like this. Okay, with the equation you can show like this, but practically means you have to draw the diagram there, you have to tell this. Okay, if you increase height, the length of the path increases through air, as it is offering very high reluctance, then some flux will be reduced. That much flux will not come in the air. Next, in the same way, width. See, one more way is what? By decreasing width of the window. Now see this. By decreasing same height, I will take like first diagram. Same height I am taking, but I will decrease the width of transformer. Same height, but same as first diagram I am drawing now. But width is little reduced. Assume that little width is reduced. So whenever width is reduced, what happened? Both windings will come nearby now. See, previously here windings, let the distance between these two windings is some 10 centimeters here. Now I am reducing the 10 centimeters to some 6 centimeters. Width reduces. Now what happening slowly here? As width is reducing, the two windings will come nearby or not? Yes, the two windings are coming little nearby. So when they are coming little nearby, whatever the leakage flux is there previously, here there is a leakage flux, but there is a chance that some flux may enter directly through air to secondary side. So if width is still reduced, whatever the flux is coming in air, it may enter into secondary winding directly through air. Now, once the flux is entered through air also, that is not leakage. It is combining with two windings, no? It is combining with two windings. So that is not leakage flux. So like this, we can reduce leakage flux by increasing window factor. How to increase window factor? Two ways: increase height of window or decrease width of window. So two methods. Clear all of you? If both increase, uh, so proportionally value required, both increase means window factor you need to check. Window factor whether increased or remains same or decreased. Okay. If any one increase, easily we can justify this. Now, see, high voltages means there is no any limit for this high voltage. 11 kV, 33 kV, or 66, 132, 200, 220, 400, anything. High voltages, these are all. For high voltages, we use mostly core type transformer. But for low voltage applications like 400 volts, these are all shell type transformers, low voltages. Okay. So these are some important differences between core type and shell type transformers. Suppose if they given any numerical like with respect to window factor, then how can you answer? You should remember this. Suppose they given there are four transformers having different window factors. Transformer A, transformer B, transformer C, transformer D. Four transformers are there with a different window factors. 0.92, 0.87, 1.02, 1.27. Now, out of these four transformers A, B, C, D, which transformer is having more leakage flux? Tell me. Which transformer having more leakage flux? More leakage flux out of these four A, B, C, D. Which transformer having more leakage flux? Yes. Yes, enough. Transformer B is having more leakage flux because what is the relation between these two? Window factor inversely proportional to leakage flux. Inversely proportional to this. If leakage flux is more means what is the window factor? Very less. Now which one having the least leakage flux here? Window factor here is 0.87. That is transformer B. So transformer B will be having more leakage flux because its window factor is very small. Okay. Okay. See, this is about transformer core. Up to this transformer core it is. Now we will go to the second one, transformer winding. KVA rating depends on both voltage and current. So high voltages, we cannot say directly. That depends on size of transformer also, based on the size of transformer and number of turns and type of copper winding we use. So KVA rating directly we cannot decide here, with voltage rating only. So different sizes of transformers will have different flux densities, and when density also change, KVA rating will change. Next, transformer winding. Second, transformer winding. The second part of construction is transformer windings. Okay, first let's see about material. What type of material we are using? High conductivity material, because with high conductivity currents will be more, resistance will be less, so losses will be less. Now we have to use copper material for this copper. So preferred one is copper. Aluminum also there, but aluminum we use at distribution side, but not in machines. So copper material we use for windings, that may be transformer windings or any machine windings. We use copper material only. So material is copper, that is clear. But what type of conductor we are using for windings? So this is important. Type of conductor. So as an electrical engineer, you must be clear about the type of conductor first. But most of the people are not aware of this. They know, but they don't know what it is. Type of conductor. What type of conductor we are using in machine windings? Everything, transformers and any rotating machines. What type of conductor we are using? Suppose transformer windings first. Tell what type of winding conductor we use. What are the type of conductors first? Types of conductors. So mainly we have solid conductors, stranded conductors, composite stranded conductors, composite stranded conductors. Fourth one, bundle conductors. And one more is that hollow conductors, but mainly these four majority we use. Solid stranded conductor, composite stranded conductor, bundle conductors. Now tell me, out of these four, what type of conductor we are using in transformer windings? What type of conductor we are using in transformer windings? Okay. Yes, okay, enough. Okay, enough. So the type of conductor we are using in machines is 90% 90% stranded conductor. Mostly 90% transformer windings completely stranded conductors. And induction motor, at in one of the case we use solid, and synchronous machine mostly stranded. At one of the place only we use solid. So you should know about these conductors first clearly. What is solid conductor? What is the use? Where we use? Why we use? All this. So solid conductor means, maybe everyone knows, solid means single solid conductor. Solid, single wire, thick wire. Now like this. Solid conductor. Single solid conductor. Now what is advantages and disadvantages of that solid conductor? Yes, there are some advantages. Solid means What is the cross sectional? If you take the front view of this front view, this is solid conductor, single solid conductor. Now what is the cross sectional area of this? More cross section. Solid, no, more cross section. So if it is having more cross sectional area, what is the resistance of the solid conductor? Rho L by A. As area is more, resistance is small. So thick wire will have low resistance always. Advantage is what? Low resistance. Then I square R loss is less. Voltage drop also less in the conductor. So that is advantage. And solid conductor is mechanically strong. It never break also. We cannot break directly it is. But small thin wire we can break. But solid conductor we cannot break directly. Okay. So these are some advantage. But there is some disadvantage also. What are the disadvantages? Whenever an alternating current is passing through a solid conductor, then most of the current will concentrate on surface of conductor. What is that effect we call? Skin effect. In a solid conductor, if an alternating current is passing, then most of the current will concentrate on surface only. That effect we call skin effect. Skin effect. Now, what is the problem of this? Yes, there is a problem. What is that is? If you take front cross section, this is a solid conductor. When alternating current is passing through this, where current is flowing? Mostly on surface. Now let us consider there is no current in the remaining part. No current. Only this red line, there is a current. Okay, there is a current. Actually, what is the total cross section? Very high. Total area is very high, capital A. Total area. But when alternating current is flowing, where current is flowing? Only surface. Now what is this area? Don't take total area, only that red circle area. Then what is that area of current flowing? Very small. Only small area current is flowing, not total area. So as area of current flow reduced, the resistance suddenly increase. So due to skin effect, the main problem is resistance, effective resistance of conductor increases. The effective resistance of conductor increase. Actually, previously what we said, resistance is less when there is no currents with a general calculation. But once there is alternating current, then resistance suddenly increase. So due to that high resistance, losses increase, voltage drop also increase. So this is one drawback of solid. And other drawback of solid is mechanical strength. Mechanically strong, no, it is. Then can you make a winding or coil like this? Suppose if it is transformer core or limb, if it is limb, can you make that solid conductor like a coil here easily by hand? No. By hand you cannot make coil it is. You cannot make like circulars. It's very difficult. You cannot make a coil by solid conductor. It is very, very difficult. Due to this reason, solid conductors not suitable for coils or windings. If you take rotating machines also, induction, synchronous, anywhere, we use number of coils. One coil having 100 turns. Like that, we make coil here. Now, can you make coil like this? No, because strength is more for this. So not suitable for coils or windings. Okay. Due to this reason, we don't prefer solid conductor. Now, where we use solid? Yes, in electrical machines, we use solid conductor at two places. What are the two places? In machines, at two places, we use solid conductors. They are, one is induction motor. At one place in induction motor we use, and second is synchronous machine. At one place in synchronous machine we use. Where is that? Maybe some of you know that. Induction motor, we have two types now: squirrel cage induction motor, slip ring induction motor. In squirrel cage induction motor, if you remember, what is the rotor winding? Copper bars are inserted in the slots. Copper bars are inserted in the slot. They are solid conductors. So rotor winding, rotor winding. of squirrel cage induction motor. Squirrel cage induction motor is solid conductor. That is one place. And in synchronous machine, where we use this? In synchronous machine, where we use? Yes, damper windings. Damper windings. If you remember, maybe those who completed the machines in your engineering, you will know that damper winding of synchronous machine. Damper winding or damper bars we call. Damper bars. That is also copper bars only, solid. So in these two places only we use solid conductor. Okay. This is in machines. So if you go outside the machines in power system, for some of the bus bars or in grids, some of the places we use solid conductors there. And neutral grounding, neutral or earthing, solid conductors we use na, for neutral grounding or earthing purpose, solid conductors we use solid. So in that places we use. And one more majority use of the solid conductor is, maybe you people know, uh, if you remember, overhead lines of trains, overhead lines of trains. If you observe, what is that conductor? Two conductors will be there overhead. See. So in the overhead lines, we have these conductors. If you remember, two conductors will be there like this. Okay. So what is this conductor? So anybody observe the overhead line or overhead conductors? These are solid conductors. Solid. Little your exactly means you can consider it is more than your pen size, not that much small one. Approximately 1 centimeter diameter will be there. 1 centimeter diameter. That's solid conductor it is. And solid, it is made up of copper. It is made up of copper. Okay, then why we are using solid conductor here? How these trains are taking power from the lines? Just by contact. Just by contact with this. What is this device we call? This is one of the question in many competitive examination. And what is the device to collect the power? We call pantograph. Okay. Yes. Pantograph it is. What is pantograph? Pantograph means it is not instrument to draw the graph, because some people will think like that. This is a device or contact used to collect the power from the conductors in the trains. And these conductors are solid. Why we use solid particularly here? Yes, solid only suitable there. Why solid? How that conductors looks like? Exactly straight line only, no? Exactly straight line. Then only the pantograph will be uniformly contact with that. Otherwise, if it is thin wire, if line is like this with some waves, then pantograph will not contact with that. So that conductor should be mechanically strong, because that pantograph will go and touch tightly with that. That's why solid conductor only suitable here. No other conductors. Like that, at some places we use solid conductors. Okay. So this is about solid conductor. In machines, only at two places we use. So you should remember all this. In machines, at two places only we use solid conductor. And why it is not suitable for remaining windings? Because remaining windings are having some turns or coils having some number of turns. So number of turns means it is difficult to make a turn by solid conductor. That's why it is not suitable. In DC machine, we don't have any solid conductor because no use. So wherever it is required, based on our requirement, we placed. DC machine not required. Armature winding, field winding we have. So they are standard conductors only. No need of solid conductor there. Okay. So this is about first one, solid conductor. Next, stranded. What is stranded conductor? Stranded means previously we taken single solid conductor, no, big one. Now You make that big solid conductor into a number of thin wires. Let's make the big solid conductor into number of small thin wires, just like solid core, laminated core. Solid core, laminated core. However, we have now in the same way, solid conductor is converted to stranded conductor. Thin wires, small thin wires, and then twist all the wires together. Then completely we call stranded conductor. What is the need of twisting? Just to give mechanical strength. Otherwise, yes, a small thin wire if you take, is it mechanically strong? No, you also can break that small thin wire. In your home also you are using home wiring, completely stranded conductors there. So thin wire is mechanically not strong. If you want strength of these conductors, number of wires you need to twist. Okay. Now where we use stranded conductors? All transformer windings, induction machine, stator winding and rotor winding except squirrel cage, and synchronous machine, armature winding, field winding, DC machine also armature winding, field winding. These are all stranded conductor. All stranded. Okay, because thin wire mechanically not strong, easily you can make a coil turns, number of turns. By hand also you can make turn easily. That's why it is suitable for windings. And what is composite stranded? Composite means mix. Stranded conductor means number of thin wires. Composite stranded also number of thin wires only, but here we will mix more than one material. See, stranded conductor, let us assume all wires. So each one we call strand here. One wire we call one strand. All the strands are made up of either copper or aluminum. All made up of either copper or aluminum. But in machines, we don't use aluminum. In if you see in your street outside distribution wires, they are aluminum only. They are standard conductor only. So that is having number of thin wires twisted. And if you see transmission lines, there we use this composite stranded conductor. This composite stranded we use in that outer wires, whatever we have number of wires, these are all aluminum, and inside one conductor or one strand is made up of steel. What is the example for this? ACSR, ACSR conductor. So those who completed transmission lines in your engineering, you people know about ACSR. What is ACSR? Aluminum conductor, steel reinforced. So at the center we have steel. See, some conductors are aluminum and inside we have steel. Inside we have steel. This is called composite. Like mixing, more than one material will be there. Aluminum is there, steel also there. Then why we use this composite standard in transmission lines? Yes, it is required in transmission lines. The reason is what? In transmission lines, what is the distance between two towers? Distance between two towers. So the distance between two towers is very high, in the range 100 meters, 100 meters or 120 meters distance. Long distance will be there. Now, in order to hold the transmission lines between two towers, definitely we required, see, this is one conductor, this is one conductor, we need to hold this from here to here. So length is very high, very big, in the range 100 meters for example, or 120 meters is there. So 120 meters means so much long it is. Then in order to hold this conductor from this point to this point, if you take only standard conductor aluminum, now what happened? So at the time of placing the conductor, it will be like this. It won't get straight line because of weight. Now it won't get straight line. There is some sag. This is what? Sag of the line. Some sag will be there. If it is only aluminum, what happened? Aluminum is not strong one. After some 1 month or 2 months, if you come back and if you see, the sag will increase. Sag increase because aluminum gets stretched because of weight concentrating at the center of this conductor. Now after some months or some days, means definitely you need to come on one day because there is some problem in the supply, because this wire has break. Why? Continuously stretching and finally it breaks. This is the problem of stranded aluminum conductors. In order to avoid this problem or to reduce the sag, what we do is ACSR we use. Steel we use at the center. So what is the advantage of that steel at center? Mechanically strong, no, it is steel. That's why ACSR we use to reduce sag in the lines. And bundle conductors also we use in transmission lines. Okay, you will see clearly again in transmission line all this. Just brief idea given what type of conductors we have and what we are using in machines. Okay, clear all of you this? So which one we are using now in machines? Standard. Mostly we use standard conductors. Okay, let's see now about transformer. This is winding material and type of conductor we have seen. Now let's see how to place these windings on the core. Now we need to place this winding on core, both the core type transformer, shell type transformer, and what procedure we apply to place exactly that winding on both core type and shell type transformer. Let's see that. Let's side heading. Placement of winding on the core. Placement of winding on the core. Both the core type transformer, shell type transformer. So I'm considering first one, core type transformer. Core type transformer. So first we will see definitions, then we will take exactly practically how we place windings on this core. So this topic is important. The transformer winding, particularly core type transformer, placement of winding important. For every competitive examination, mostly we have many times question on this topic, placement of winding on core type transformer particularly. So considering a core type transformer, core type. Now, up to now, we are drawing every diagram like primary winding on one limb, secondary winding on other limb, like this. So generally, we are drawing every time this diagram. But practically, how we place winding on the core is, so we don't place complete winding on one limb directly. So how we place is, observe this. Suppose this is LV winding, this is LV. Half LV we place on one side and remaining half LV we will place on other side, like this. This is half LV winding here. Suppose LV winding having 100 turns, HV winding having 200 turns. Now half LV means how much? 50 turns. 50 turns here, 50 turns on other limb, not on same total it is. Now HV winding also same procedure. See, HV winding. Half HV is here and remaining half HV on other side. Like this. This is half HV winding and here remaining half HV winding. So like this we place. And finally outside we bring two terminals for LV, two terminals for HV. No, that is two final ends for LV winding and two ends for HV winding. Now we will bring that windings like this. Suppose I am taking LV is primary side. Any terminals you can take. LV I am taking primary side. So these two I will take here. And HV I am taking as secondary side. Okay, this is secondary side. So output, these are output terminals and these are input terminals. Source is connected here. So half LV, half HV. So this type of winding procedure, is called concentric and interleave winding procedure. Concentric and interleave winding procedure. Concentric means exactly half LV, half HV on one limb. This is half LV, half HV, one limb, and remaining half LV, half HV, other limb. Interlink between these two limbs. So this is called concentric interleave winding procedure. Now, what is the need of this winding procedure? Yes, why we are using this procedure is mainly to reduce leakage flux. To reduce leakage flux in transformers. To reduce leakage flux. To reduce leakage flux in this transformer. Leakage flux is reduced? Yes. Previously we have seen in magnetic circuit, no, core type, the windings are separate limbs, then more leakage flux is there. But now what happened? See, LV side I'm giving supply, current is flowing, flux is produced. Now in that some flux is leakage, but now some part of secondary winding also there here. HV is secondary, no, some part of secondary is on the same limb. Now what happened? Some of the flux may enter directly through air itself. Now this is not leakage, no. Yes, like that leakage flux we are reducing by placing half LV, half HV on one side. Leakage flux will reduce with this. So mainly to reduce leakage flux, we are using this type of winding procedure in core type transformer, concentric and interleave winding procedure. Okay. So write one statement there in your book. In core type transformer, the winding procedure used is concentric and interleave. Concentric and interleave. It reduces the leakage flux in transformer. It reduces the leakage flux in transformer. To reduce leakage flux in transformer. Now, this is definition only, just half LV, half HV we placed on one side, half LV, half HV on other side. But practically, whatever the figure you are seeing now, half LV, half HV we place, but not like LV is top side, HV is bottom, and HV is top side, LV is bottom side. Not like this. There is an exact practical procedure that we will see now. Okay. For this, we will take one example, one small transformer we will take with some rating, and that winding we will place in transformer core. How it is observed. Consider example it is. Example. Practically like this only we place. Consider a single phase transformer. Consider a single phase transformer of rating. So I'm taking, for example, 6 kV by 3 kV. Just a small rating I taken, some rating, voltage rating. High voltage is 6 kV, low voltage is 3 kV. 6 kV by 3 kV. This is HV and LV. Now this is we need to place on transformer core. Now see how we place. Try to draw a little big diagram. Before placing any winding on the limb, what we have to place on that? Insulating material throughout that, because directly winding you should not place on the core, they may get short circuit again. So to avoid that, first insulating material we have to place throughout the core. Okay, so first insulating material I'm placing. This is insulating material. So some, you can consider that some papers like impregnated papers I placed here with some thickness of this insulating material. This is insulating material. And how much to be placed that insulating material, or how many papers, for example, you need to place that insulating material, how much we need to place? Can you place whatever we want? No. So there is some calculation for this also. Directly you don't place whatever you want the insulating material. If you place more, no problem. But if you place less insulating material, no, then there is a problem of short circuit of windings. So to avoid that, we need to calculate the dielectric strength of that insulating material before placing on that. Now, before placing this insulating material, first you need to decide which winding you will place first, half LV or half HV. Which is we prefer to place, LV winding or HV winding. So we prefer to place always LV winding. So these are only the question. So I will tell some advantages. In the advantages only, we have questions in many competitive examinations. Regularly, we have questions in ISRO. Many times there is a question on this topic on advantages. What is the advantage? In engineering services also we have questions many times on this winding placement. See, first, what is half LV means? Half LV. LV is total 3 kilovolts. Half LV means 1.5 kilovolts. And what is half HV? HV is total 6 kilovolts. Half HV means 3 kilovolts. Now, we need to place this winding on this core. So I prefer to place LV first. Now, after that, I will take HV. What happens? I will give you the information. Okay. Observe this diagram. First, I am placing half LV directly. Half LV directly. Then I will tell how much insulation we need to place. This is half LV winding. Half LV winding it is. Half LV winding means for half LV, what is the voltage? 1.5 kilovolts. So accordingly, how many turns required we will place. So this is half LV winding. LV winding it is. And what is this insulation we call? This is we call LV insulation, because LV winding is placed now over that. Now, how to place that insulating material is, and one more I want to tell, people will get doubt. So you said winding, but you are drawing these rectangular boxes here. What it means? See, actually winding we place like this on core. according to the figure like this. Like this we place windings, but here like this we cannot draw here in this diagram, because LV winding, HV winding, both I have to place here. For that reason, I am not drawing winding like this. Like this, I'm not drawing. So I'm drawing like a box. So this box indicates some turns, LV winding turns are there. Okay. Now see this. This is LV winding. What is the half LV winding voltage? 1.5 kilovolts. Now, how much insulating material we have to place is, we always consider this core is at zero potential. We will assume this is at zero reference, 0 volts it is. Now, what is LV winding voltage? 1.5 kV. So 1.5 kV minus 0. This is core 0, no? What is the difference between these two? 1.5 minus 0 means 1.5 only. So you have to place insulating material of dielectric strength. In what? How we measure insulating material? In what we measure insulating materials? In terms of dielectric strength. If you consider like impregnated papers, no? One paper thickness is assume 0.5 mm. One paper thickness 0.5 mm. This 0.5 mm can withstand voltage of 0.5 kilovolts, means 500 volts. One paper will withstand 500 volts. Then how many papers we need to place here? Total 3 papers we have to place, one over other, 3 papers. Some thickness you get. So that much thickness of insulation we placed. Because how much strength required? Total 1.5 kV strength required. So how many papers you need to place insulating material? 3 papers you need to place there. So that is we placed first. Okay. Suppose if you place HV winding first, then what is half HV voltage? 3 kilovolts. Then how many papers you need to place? 6 impregnated papers you need to place. Then thickness of insulation increase or not? Yes, increases. So like that it depends. Thickness of insulation will change if voltage rating is changing. Okay, so anyhow, half LV we placed, LV winding. Next, again what we have to place? Can you place directly HV on that? No. First core limb, insulating material, and then LV winding on that, number of turns. And can you place directly HV now? No. Again insulating material, again some papers on that, again then HV winding we have to place. So again we have to place insulating material throughout this, insulating material. This is we call HV insulation. Over that we place HV winding. HV insulation it is. Now over that insulation place HV winding. This is our HV winding. So this figure is very important in the conventional examinations. For GATE or any objective type of examination, these are all not required. So that's why I'm giving information those who attempt the conventional in future. Figure is very important for conventional. Okay, this is HV winding. What is important here is, see, HV winding I indicated with dot, small dots, but LV winding I indicated with small circles. Means what? HV winding is thin wire or not? Yes, in the first class I said HV winding made up of thin wire, LV winding made up of thick wire. See, I written here anyhow LV winding, HV winding. So even if I don't write LV, HV here, you should understand this is LV winding, HV winding. Okay. Don't change that circle and dot here. If you interchange, your figure is wrong. Even if you write LV winding, HV winding. Okay. Now, how much HV insulation we have to place? What is the HV winding voltage? Half HV, 3 kV. And already there is a LV winding here, 1.5 kV. Now, this winding, HV winding is 3 kV and LV winding is 1.5. What is the difference in these two? 1.5 kV. So the HV insulation is 1.5 kV. So this is also 1.5. means 3 impregnated papers again you have to place, and on that HV winding. Okay, so like that half LV half HV on one side is complete. Same procedure you have to do again on second limb, half LV half HV, same diagram, just copy and paste here. Okay, so anyhow not required, but in the examination you have to draw completely both sets. Okay, so like this we place winding on the core. Now let's see what is the problem if you place HV winding first. We always preferred LV winding only. First we place LV winding on the core, then only HV winding. Now what happened? First see, when you place LV first, total how much insulation we required? LV insulation 1.5 kV plus HV insulation 1.5 kV. So what is the total insulating material required in this case? Total 3 kV insulating material required. But suppose let us consider HV is placed first. I'm not placing, you have to answer directly. Okay, HV is placed first. HV is first. So if you place HV first, HV will be 3 kilovolts. Core is at 0. Then what is potential difference? 3 minus 0. Then how much insulation you have to place here first? 3 kilovolt insulating material you have to place. 3 kilovolts means 1 impregnated paper 0.5. Just example I given. 3 kV means 6 papers you have to place first on the core to withstand that voltage. Okay, if you place HV first, initially we have to place 3 kilovolt insulating material. HV first core, then insulating material, then HV is placed, and over that again insulating material you have to place, and then LV winding. HV is 3 kilovolt, LV is 1.5 kilovolt. What is the difference in these two again? 1.5. So again how much insulation we have to place there? 1.5. So total how much insulating material now? 4.5 kV. Therefore if you place LV first, how much insulation? Only 3 kV. But when you place HV first, 4.5 kV required. Then what happens due to this? Cost is less here, but cost increases. Not only cost, there are some advantages of LV. So that advantages we will see now. Okay. So completed all of this figure. First complete the figure, then we write advantages. Why we have to place LV winding near to the core or first on the core? Because of some advantages. Let's see what are the advantages. Right, starting. Advantages of placing advantages of placing LV winding near to the core. LV winding near to the core. So what are the advantages of placing LV winding near to the core? So write the first advantage. First advantage. What is the first advantage? Just now we have seen the insulation required is less. Right, first one. The insulation required is less. The insulation required is less. Second. Now observe carefully now. Insulation reduce. Thickness reduce. No. Whenever insulation is reduced, for 1 ton, how much copper wire required? Less copper wire required. No. For 1 ton, copper wire required is less. Otherwise, if you place HV first, more insulating material you have to place. Then diameter increases over the limb, diameter increase. Then for each turn, you need to take more copper wire. So when you place LV, as insulation is reduced, the diameter on the limb reduced, so that for 1 ton copper required is reduced. Like that, if there are 1000 tons, so much copper will be saved. So this is one advantage. Write that point. The copper required, the copper required for each ton, reduces. Why copper required reduce? Since diameter is reduced. Write that point. Since diameter is reduced, diameter is reduced, so that less copper is required for 1 ton, each ton. Next, so as insulation is less, copper also less, then due to these two reasons, what is the main advantage? Cost reduces, size reduces, right? Due to above reasons, due to above reasons, the size and cost of transformer reduces. Size and cost of transformer reduces. Size and cost of transformer reduces. Next, fourth advantage. Fourth, see this fourth advantage is when you place LV winding first, insulation is less. Means if it is limb, what is the distance between winding and the core? Less only, no? Because less insulation, less diameter, the distance between winding and core is less. Otherwise, if you place HV first, then what is the distance between winding and the core? Increases. So whenever there is more distance, leakage flux will increase. More distance, leakage flux increases. But as winding is near to the core, as winding is near to the core, air gap is less, so leakage also less. So that is one advantage. So if you place LV winding first, the windings are nearer to the core. Due to that, leakage flux in transformer is reduced. So write that point. As windings are nearer to the core, as windings are nearer to the core, nearer to the core, the leakage flux reduces. The leakage flux reduces. Okay, the leakage flux reduce. So in previously ISRO examination also same point. So they given like if we place LV winding adjacent to the core, if LV winding is placed adjacent to the core, which of the following will reduce? Which of the following will reduce? Like that, in that one of the option is leakage flux. Leakage flux will reduce if you place LV winding adjacent to the core or near to the core. Next, one more advantage. Fifth one. So this is regarding tappings on transformer. Tapping. This is regarding tappings. What is the need of tapping the transformer winding? Yes, we need to tap sometime. What is the need to tap? Tappings we use. See, for example, I'm taking, there is a transformer of rating 200 by 400 volts, for example. This is a 200 by 400 volt transformer. This is LV, this is HV. Now, if it is required, so I required, for example, only 250 volt. I don't want 200, I don't want 400. My load will work properly with 250 volts. Then can I get from this? Directly I cannot, because the rating of this transformer either 200 or 400, but 250 is not there. So if I want 250 volts, I need to tap one of the winding. Then generally we prefer always HV winding. So this is total 400. No, now 400 volts it is. So I will tap at one particular position so that I will get 250 volts here. And if I want 150 volt, so I will tap somewhere here. So I will get 150 volts also. Like that, For any voltage rating, if you want, you need to tap the winding. Just tap the winding. Now you may get doubt. For 150, why 200 is not tapping? We preferred the tappings always on HV side, but not on LV side. HV side tapping is preferred. Why we preferred HV side tapping? Tell me. When there is low voltage, what is the current rating here? High. When there is high voltage winding, what is the current rating there? Less. Current rating will be less here. Magnitude of currents are less. So during the tapping, as current is less, you will get less spark at that time. Spark will be less. So whenever you are tapping now, during tapping, as current passing through the winding is small current, spark magnitude is less. So no problem you will get. But if you tap on LV side for 150, if you want 150, if you tap on LV side, what happened? High currents are flowing in this, high current. So when you tap LV side, as high currents are passing through the winding, the magnitude of spark will be more. So sometimes because of that heavy spark, the winding also may damage. So this is one reason why we are tapping on HV side. And other reason is what is the range of voltage you will get on HV side if you provide tappings? 0 to 400 volts. Any voltage you can get. 50 volts, 70 volts, 90, 150, 210, or 310, or 350, up to 400, any voltage you will get. But not on LV. No? What is the range for LV? Only 0 to 200. So this is one reason why we prefer tapping on HV side. And the main reason why we prefer tapping on HV is according to our winding procedure. Which winding is outside the limb? Which is outside? Which is visible to you directly? HV is visible for us. HV outside. If it is limb, first insulation, LV winding, again insulation over that, and then HV winding. So HV winding is final. So at the outside, HV winding is available. Now easily you can tap this. Easily you can tap. Taps. If it is required to provide tapping for LV, is it easy to provide tapping? No, because it is totally covered by insulation here. We cannot provide easily. Very difficult. So due to this reason, HV winding we always prefer to tap. So write that point. Write this. The tappings are provided on HV winding easily. The tappings are provided. Tappings are provided on HV winding easily since it is outside. Since it is outside. It is outside. So HV side we need tapping easily we can provide because HV winding is outside, no, LV inside. So these are the advantages of placing LV winding near to the core. Yes, tap means just touch, contact. Just like auto transformer knob tapping is there, no? When you rotate the auto transformer knob, different turns, voltage rating will change in the same way. How leakage flux will reduce? When you place LV, how much insulation is required total? Just 3 kilowatts. Means as insulation required is less now. If you place LV, now windings will be near to the core. Less insulation, less diameter, winding near to the core. More insulation, more diameter, winding will go away from the core. So whenever winding is more away from the core, more gap will come. Then leakage flux also increase. But if you place LV, winding is nearer, so leakage flux is reduced. Okay. If you want tapping on LV side during the construction, during the design placement of winding itself, tappings should be provided, and that tapping position wires should take outside. But in between you cannot tap. So generally after completion of construction, you cannot tap, no. The tapping should provide inside the core transformer tank, and that windings is provided outside in a terminal box. Then only we can provide tappings, whether it is HV winding also. Okay. Okay. So these are the some main advantages of placing LV winding near to the core. No, the thickness of HV winding and LV winding is different, no, because based on the current rating, we decide the winding thickness. Number of turns will decide voltage rating. Thickness of wire will decide the current rating. Okay, both are not same. Okay, make a note or write the side heading regarding this. Then we come to the same figure again one more time. Right. Force between current carrying conductors. One second. Force between current carrying conductors. Force between two current carrying conductors. Two current carrying conductors. So here the two current carrying conductors may carry current in same direction or may carry current in opposite direction. Then see what happened here. First, if two conductors carry current, if two conductors, so they are adjacent, then only it is. If two conductors carry current in same direction, then what will be the force between the two conductors? So suppose like this. This is one conductor, let I1 current and current I2 in other conductor. Both are adjacent to each other. Both are adjacent. Two conductors carrying current in same direction. Then what is the force acting between two conductors? Force. What type of force? Attractive force or repulsive force? So there will be a attractive force between the two conductors, because apply right hand thumb rule for this. For each conductor separately, current is upward direction, flux is rotating around that conductor. Now this is our flux direction. Flux is going inside, coming outside. It is going inside according to your thumb, right hand thumb rule. Four fingers going inside, coming outside, because the current carrying conductor is in your grip, inside the grip, and thumb indicates current direction. The four fingers indicates flux direction. So this is our current coming outside, flux it is. In the same way for second conductor, current going, flux is going inside, coming outside, coming outside. This is flux. Now, what is the force acting between two conductors? So there exists a attractive force. There exists an attractive force. So simply you can remember by observing the polarity of flux here. This is cross, this is dot. You can simply remember like this: cross and dot here, cross dot, opposite polarities. These two conductors gets attracted each other. So attractive force exists between the two conductors. Attractive force. Then there is an attractive force. An attractive force between conductors. Between conductors. Okay, next. This is first point. Now, if two conductors carry current in opposite direction, then there will be repulsive force. In the same way, if two conductors carry current in opposite direction, I1, I2, then what is the force acting between the two conductors? Here, if you apply right hand thumb rule, this is flux direction, going inside the paper, coming outside, dot. And second one, current is downward direction. Apply your right hand thumb rule. Thumb indicates current direction, and flux, four fingers indicates four fingers. So here it is going inside and coming outside, dot. This is the flux direction by right hand thumb rule. Now same polarities we got, same polarities. So you can consider same polarities of field gets repelled, opposite polarities attracted. So these two gets repelled here, same polarities repelled. So there exists a repulsive force between two conductors. Repulsive force between two conductors. So write the second point. Second point. If two conductors carry current, if two conductors carry current in opposite direction, in opposite direction, then there exists, then there exists a repulsive force between conductors. A repulsive force between conductors. Okay. Now these points, whatever we have seen now, we will apply to transformer diagram now. Observe what happens between the windings. The same thing we are applying now to transformer windings. These 2 points. So if two conductors carry current in same direction, attraction. If two conductors carry current in opposite direction, repulsion. Now same thing we are applying. See the diagram again one more time. See this. First of all, I will take individually the two cases. First, initially we have seen the windings are placed on separate lanes. Then we have seen practically that half LV, half HP one side. Two windings are placed on same lane. Now I'm considering that first one. If if two windings are placed on separate lanes, if two windings are placed on separate limbs. Separate limbs. Then see what happened between the two windings and how they should carry current. Current direction for we need to find here. So two windings are placed on separate limbs. LV winding on one limb, HV winding on other limb. Let here LV winding is placed like this, and HV winding is placed here. Assume that this is LV winding, this is HV winding. Two windings are placed on separate limbs. Now, how they should carry current? How they should carry current first? Same direction or opposite direction to satisfy Lenz law. LV winding I am taking as a source side, so I will give source to that, current will flow in this. So how current is flowing? Let I'm considering current is flowing like this. Current cross dot like this. Current is going in the winding, LV winding, cross dot. Current is going inside this side, and current is coming outside. So like this, current is moving in the LV winding. Now apply your right hand thumb rule. Cross dot. Flux is coming in upward direction. Okay. This is the flux produced by LV winding by right hand thumb rule. Now, according to transformer action, according to Lenz law, what should be the flux produced by other winding? Opposite to this. So I will take directly, according to Lenz law, the flux should be opposite to LV. If LV is coming in this direction, HV is opposite. The flux due to HV winding is opposite direction. Okay. So it should produce flux in this direction. Now, according to flux direction, you try to find current by applying right hand thumb rule. Flux should be upward direction. Now apply your four fingers there. So four fingers are going inside here. So cross, and four fingers coming outside from the back. It is dot. Okay. So if two windings are placed on separate limbs, how they are carrying current? Same or different? Same direction. No. This is cross dot. This is also cross dot. Same direction current is flowing. So right here, if two windings are placed on separate limbs, then they should carry current in same direction. This is also one of the objective question in so many PSUs. Then they should carry current in same direction. They should carry current in same direction. Okay. This is first case. Now what we have seen, we are placing both windings on same limb, half LV, half HV. Now what should be the current? We need to calculate first. Okay. Second point. Second. Completed. See the second point. If two windings are placed, on same limb, then what happened? So I'm considering now the two windings are on same limb. Two windings are on same limb. So this is half LV winding and this is half HV winding. LV, HV. Okay, LV, HV. Now LV side, I'm considering source. Source is given, current will flow in some direction. So that is our wish. You can take any current direction. So I'm taking cross here, dot here. Okay, cross dot. Cross dot. Apply right hand thumb rule. You will get flux direction there. How the flux I am getting? You are getting downward direction. No. Four fingers is current direction. Thumb indicates flux direction. So flux due to LV winding is in the downward direction. This is flux due to LV. Okay. Now, what should be the flux due to other winding? Opposite to that. To satisfy Lenz law, it should produce flux opposite direction. So I'm considering this is flux due to HV winding. Opposite to that. Now, according to that flux direction, HV flux, you apply right hand thumb rule again. Thumb indicates flux direction and four fingers is current direction. Then I'm getting current, my four fingers going inside here and coming outside here. Right hand thumb rule is applied. So both the fields are opposite, satisfying Lenz's law. Then observe what is the current direction we got for two windings. Same or different? Different. So both are carrying current in opposite direction. So if two windings are placed on same limb, then they should carry current in opposite direction. Write that point. Then they should carry current. They should carry current in opposite direction. They should carry current in opposite direction. Okay. So these 2 points we will apply in the diagram. Okay. So I will give break because little continuation is there. With this, this topic will complete. No, that's fine. Just 2-3 minutes. Okay. Now see the figure for actual winding diagram. This is observe here. So we are placing exact winding like this. So when you place two windings on same limb, they should carry current in opposite directions. Just now we have seen. Now I will apply here. See, this is first one is what? LV winding. First one is LV winding. So I'm considering this is cross, this is dot. Okay, in LV winding, current is flowing like this. In LV winding, current is flowing like this. Flux due to LV winding is in upward direction. Okay. Now in HV winding, what should be the current? Opposite. Then only flux is reverse. So in HV winding, current should be opposite. Cross here, dot here. Then flux due to HV winding will be opposite. Okay, same thing we applied here. The two windings should carry current in opposite direction. Now only the important point. For this, we are doing all this. Now observe, if two conductors carry current in opposite direction, then what type of force is coming between the two conductors? Repulsive. If two conductors carry current in opposite direction, there exists a repulsive force. Now observe, LV winding. LV winding means this is one conductor, like this is HV winding, other conductor carrying current in opposite direction. Therefore, there exists a repulsive force between two conductors. So after placing the two windings, when they are carrying current now, there exists a repulsive force. There exists a repulsive force between two conductors. Between the two windings, repulsive force. But we no need to worry about repulsive force here under steady state operations. Steady state means the MMF of LV winding, HV winding balanced. So force produced by both windings is balanced on both the sides. So whether it is repulsive force also, it won't damage the winding. Winding will not damage. But under fault conditions or transient condition. So we have one topic switching transient condition, sudden variation or fault condition, suddenly currents increase. During that fault condition or transient condition, there is a problem with repulsive force. Now what happened if repulsive force occurs? Which winding is outside here? HV winding is outside. So if it is limb, LV winding inside, HV winding outside. Whenever force is acting, because of repulsive force, one of the winding is trying to dislocate. Which winding? That is HV winding. So therefore, due to repulsive force, under abnormal conditions, write this point. Under abnormal conditions, due to repulsive force, under abnormal conditions, the HV winding will try to dislocate from its original position. From its original position. From its original position. Means what? HV winding is at one location actually, but due to repulsive force, it is trying to go out from the core, going away from the core. So what happen if winding is trying to move away from the core? Some gap increase or not? Yes. When gap increase, leakage increase, then power transfer will reduces. So there is some problem. Then how to protect that winding from repulsive force? Yes, we need to protect. Due to repulsive force, as it is trying to go out, we need to attach tightly to the core. How? For that we use clamps. Clamp support we give, mechanical support. So we need to provide a mechanical support to the HV winding so that it should withstand from the repulsive force. It should not go away from the core. It should be towards the core always. Okay. So right here, note to withstand from repulsive forces. Write it. To withstand from repulsive forces, the winding should be provided with a good mechanical support. The winding should be provided with a mechanical support. Okay. So with this transformer winding, core type is completed. Core type. And winding placement on core only we have seen. Shell is there. Shell is just 5 minutes topic, that is. So once shell type is complete, then we go to actual operation of transformer. Okay. From there it will start. Exactly. Construction will complete now. Then we go to actual operation of transformer. After completion of that shell type, just 5 minutes it is. Then we start operation of transformer. Okay. Take a break. So let's see one question. See this question. Tappings are normally provided on high voltage winding of a transformer only because of dash. So why we provide tappings on high voltage side? Due to some advantages. Low currents will be there, spark magnitude will reduce, and range is more, and HV winding easily available. No, outside it is easily we can tap. LV is inside, very difficult to tap, but HV winding easily we can tap. So read the options. It has larger number of turns, which allows smoother variation of voltage. Yes, it is right. It has to handle low currents. Yes, high voltage winding is low current we need to handle here. And it is easily accessible physically. Okay, and D, if you observe all the three options given in this, so option B is correct. Okay. Mostly in the construction part, you will get only theory questions because we don't have any numerical type of questions. So it will start from the next topic, numerical questions mostly. Let's see the last one in the transformer construction, that is transformer winding core type we have seen. Now let's see shell type transformer. Shell type. In shell type, how we place winding on the core? So what is the core type winding procedure? Half LV, half HV, one limb, and remaining half LV, half HV, other limb. Why we are using like that? To reduce leakage flux in transformer. If windings are on separate limbs, more leakage flux. That's why some part, half of, if you place nearby, no, leakage flux will reduce. For that reason, we are using that. Now, in shell type, how we place? See this. Shell type transformer. How we place winding on shell type. Actually, in shell type, in the definition differences we have seen. Shell type transformer, the two windings are placed on middle limb. The two windings are placed on middle limb itself, both. So already there is less leakage flux. Now still we need to reduce leakage flux. For that, the winding procedure is like this. So LV winding, HV winding, both are on the same limb, but we don't place total LV winding at one place and total HV winding at one place. So alternatively, so we will divide the LV winding into some equal parts, HV winding into some equal parts. Okay. So for example, now I'm dividing the LV winding, total LV winding into three parts. Three parts I'm dividing. And total HV winding, I will divide into two parts, two equal parts. Two equal parts I will divide. Now, what we have to place before placing winding on any core? Insulating material. So first what you have to do is throughout this core, place insulating material. This is completely insulating material. And similarly on other side, it should cover wherever winding will touch the core, there insulating material you have to place. If winding is touching with core, there you have to place insulating material. Not only vertical link, to the yoke side also you have to cover insulating material. Now let's place LV winding. So LV three parts, no? LV by 3, that is 3 equal parts. So this is some number of turns I will place here. Some number of turns. Okay. This is LV winding. One of the part LV winding is here. Next, again insulating material, because between LV and HV, again insulating material you should place some insulating material. Again HV winding. HV winding. Some turns are placed there. Again insulating material. Layer by layer we place. This is HV winding. This is LV. This is HV. Half of HV. Again insulating material. And then one of the LV what? One is placed here and other is here. LV winding. Next, again insulating material. And then HV winding, other half. And again insulating material. And then LV winding remaining. So LV three parts now. First, second, third. Now third remaining LV winding here. This is remaining LV. So LV1, LV2, LV3, three parts. HV1, HV2, two parts. So always we have to make LV more parts, because what is the reason is the to the core always nearby LV winding only should be there. Then only insulation will reduce. For that reason, at the top side or at the bottommost LV winding should come. The part of LV winding should come. Then only insulation required is reduced. But compared to core, what is the problem of this shell type? So much insulation required. Insulating material required is more in this, because to cover most of the core part here. See, not only vertical section, horizontal also we are placing insulating material. So insulation required is more. And this type of winding procedure we called sandwich winding procedure. This is sandwich winding procedure. Layer by layer. So layer by layer, LV winding, insulation, HV winding, again insulation, LV winding, and so on. Like this continuously we place. Okay. So LV should be more number of parts, HV should be less parts, because LV should come at the top and bottom most. For that, one part will be more for LV winding always. You can make 5 parts and HV 4 parts. Okay. Like LV 2 parts and HV 1 part also you can do. And if you do more number of parts like this, what is the advantage of the sandwich first? If you place directly, no, what happened? If you place directly LV winding once, HV winding once, what happened? Actually, leakage flux is less only here. So first insulating material, and place directly LV winding first. Total LV winding at one place. Total LV winding, then insulating material, and then total HV winding here. Total HV winding it is. This is LV, this is HV. If you don't place like sandwich, directly placed LV, HV, then what is the problem is insulation required is more, because HV is touching directly the core here. This HV winding, part of HV winding touching with core. So more insulation required. It will demand more insulation. That is one problem. But main problem is leakage flux is more in this. Compared to sandwich, leakage flux increases in this. And what is the advantage of sandwich is observed. LVHV, LVHV, LVHV. Suppose if you take like LV is source is connected to LV now, then whatever leakage flux is there, definitely it will touch with the HV, other winding, because very, very near the layer by layer we placed. So due to that reason, the main purpose of this sandwich is still to reduce leakage flux. Leakage flux still reduces. Leakage flux still reduces by using sandwich winding procedure. So write one statement in this below this figure. In shell type transformer, Right. In shell type transformer, the winding procedure used is the winding procedure used is in shell type transformer, the winding procedure used is called sandwich winding procedure. Sandwich winding procedure. Sandwich winding procedure, which reduce the leakage flux, which reduce the leakage flux, which reduce the leakage flux. Yes, sir. So one of the student is asking why we don't use the winding in shell type also like core type. So core, how we use first LV winding is placed and over that HV winding is placed. Like that, why we are not using? Why we are using like layer by layer here? The reason is what is the width of the windows here? Small width, no? Because already size increased because of three limbs. Because of three limbs, already size of core is increased. So width is less here. So if you place like that, insulation, LV winding, insulation, HV winding, one over other, then more width is required. Because of that reason, it is not preferred like that. So we prefer, if you place like that, now again, HV winding will come outside. And that HV winding may touch core outside there, may touch core. So then again, insulating material increases. So that is not suitable here. That's why sandwich only we use. Okay. Why more LV parts? Just now I said no. See, I am giving totally whatever the doubts you are getting before that itself, but you should listen carefully. So why more number of LV parts? I said because at the top and bottom most LV only should come. Otherwise, if you take both two parts, first LV, HV, LV, HV. So bottommost which one is coming? HV is coming, but HV should not come. That's why we make LV three parts. Okay. HV winding is touching, but compared to that other cases, little less insulation it will take here. Yes, two LV parts, one HV part also you can take. Okay. Insulation same like impregnated papers we use. Okay. So with this, we complete construction part of transformer. So only two parts mainly we discussed: transformer core, transformer winding. Okay. Next. Now we start the actual discussion of transformer from here. If HV is at the bottom, it will touch with the core na again yoke. So there more insulation you have to place. So to avoid that problem, we are placing LV at the bottom. Always LV should be near to core. Okay, as much as possible, LV should be near to core. Then insulation requirement reduces. Okay. Okay, right. Now let's see. So before discussing the actual discussion of transformers, first we will see what are the ideal properties of transformer. Complete transformer is based on these ideal properties only. Write that ideal properties of transformer. Ideal properties of transformer. Now, complete transformer depends on these five ideal properties. Okay, five ideal properties we have. Completely from these five ideal properties only, step by step transformer will build. Now see what is that five ideal properties. The first one, ideal. So previously in the construction part, what type of core we have choose, and we have chosen the core should have high permeability. High. Ideal case, what is that high value? Infinite. So ideal case, the permeability of core is infinity. So write that point. First one, the permeability of core. The permeability of core is infinite. But is it possible practically? No. Practically, it is not possible. That's why we take now operation of transformer with the finite permeability. Infinite, not possible. Okay. This is the first one. Permeability of transformer core is infinite. Next, second, good one. In shell type, dislocation mostly will not be possible because already there is outer core is there now that will provide mechanical support to windings. So dislocation not possible in that. Next, second ideal property. So in the core itself, properties we have seen previously, the core is having some iron loss or core loss we call. What should be the iron loss? Less. The iron loss of transformer core should be less practically. But ideal case, what is that less value? Zero. Right. The iron loss of transformer. The iron loss of transformer is zero. The iron loss of transformer is zero. But practically, is it possible? Never. It never possible. There will be a small amount of loss. Next, third. Actual the resistance of winding practically we are using copper, so it is having the low resistance. And ideal case, what should be the resistance of winding? Zero. But practically not possible. So write that point also. Third one. The resistance of winding is zero. The resistance of winding is zero. Next, fourth one. Now we have seen in the types of magnetic circuit about leakage flux. Every transformer will have practically small amount of flux is leakage. And ideal case, what should be the leakage flux? Zero. There should not be any leakage flux. Ideal case this is, but practically not possible. So write that point also. The leakage flux in the transformer is zero. The leakage flux in transformer is zero. Next, fifth one. The fifth one is regarding BH curve. So maybe you are aware of that magnetization curve, or BH curve we call, or hysteresis curve we call in the magnetic materials. The shape of BH curve. What is the shape of BH curve? Practically a non-linear shape. Hysteresis loop we call, no? So if you remember that word. So the shape of BH curve practically non-linear. We call hysteresis curve it is, or hysteresis loop, or BH loop. But ideal case, what is the shape of BH curve? Linear, but practically not possible. So write that point also. The shape of BH curve. The shape of BH curve is linear. Linear like this. BH. Linear. But practically it is a non-linear curve. Ideal case it is linear, practically non-linear. So these are the 5 ideal properties of a transformer, but practically these 5 never possible. That's why now what we do, step by step, one by one we take. First we take operation of transformer with the finite permeability, because infinite not possible. And then we take second operation of transformer with iron loss, because zero iron loss not possible. Like that, one by one we take. So up to 4 points we will take continuously, but the fifth point I don't take now itself. So I will take after completion of performance parameters at the last. Just before three-phase transformer we will discuss about the fifth ideal property. Okay, only this fifth ideal property is the most important, at the same time a little not difficult, a little concentration required to understand this. Okay, so anyhow we will see this is after completion of performance parameters. Okay, after this three-phase transformers will come. On these ideal properties also we have a previous question. Let's see that question in the previous ESC. It is, see the question, which of the following would refer to an ideal transformer? Which is the answer? Ideal transformer, what are the properties? Winding resistance negligible, yes. Zero resistance. Leakage fluxes are included. Ideal means leakage flux is what? Zero. So it is not correct. Second, core losses are negligible, means iron loss is zero. Correct. Magnetization characteristics is linear, means BH curve is linear. So this is also correct. So 1, 3, 4 option B is right. Yes, right. That's why I said for engineering services, each and every point will be there in previous years. So after completion of transformer, you try to go through the previous questions once. Definitely 95% of the questions. Suppose if there are 100 questions, in that 95 questions you will answer directly just from the class notes. So no doubt in this. So every question, whatever is given, will be there in your notes. And like competitive examinations also almost same. Okay, so first be perfect in the classwork, then only go to any other books, that may be textbooks, standard books, or any materials, or any previous questions, anything, but be perfect in the classwork itself first. But most of the people, what they do is they don't concentrate on this first. They will listen here and they will practice some other, and from the some textbooks they will use different notations, and by reading the textbooks you will lose completely your information. So not required, that much is not required. Already I said our syllabus is so much vast, so whatever you are preparing here, reasoning here, that is enough. 90% this is enough. Be perfect in this first. Now considering first point here, okay, it is infinite permeability, but practically it is not possible. Now we will take that side heading. Write the side heading: operation of transformer write this: operation of transformer with finite permeability. Operation of transformer with finite permeability. Finite permeability core. Infinite not possible practically. That's why we taken finite. Finite permeability core. Now considering which is having finite or highest permeability, already we have seen in the transformer core construction, silicon steel or CRGO steel. Considering that, considering CRGO steel or silicon steel. Consider a transformer so to listen continuously, the only thing required is patience. Particularly for online classes, I said many times, like physical classes, we may create some concentration directly, but not here. So your concentration is important to listen these classes. So entertainments are not possible. Don't expect. So consider a transformer with finite permeability. Finite permeability. Now to this, secondary is under no load. We are not connecting anything to secondary is under no load condition. No load means open. Winding is open, nothing is connected to transformer. At that time, consider the primary is excited from a alternating voltage source V1 having frequency F. Okay. If it is infinite permeability, ideal case. So tell me ideal case. As it is no load, is the transformer will draw any current from source? No. No load. No load means transformer output is zero. So input also should be zero. Means transformer should not draw any current from supply. That is ideal case. But practically, is it happen? No. Even under no load, even under no load, when you excite the primary with a voltage source, sinusoidal voltage source, it will draw a small amount of current. It will draw a small amount of current from supply. That current we call magnetizing current. That current we call magnetizing current. Let the primary having turns N1, secondary having turns N2. So concentrate, important equation will come, EMF equation in this. Listen one more time. A transformer core with finite permeability is taken. Now under no load with secondary open, primary is excited from a alternating voltage source. Then it is drawing a small amount of current. This current we call magnetizing current. This current we call magnetizing. Why we call magnetizing is due to this current only the core of transformer gets magnetized. Means suppose you if you don't connect source here, observe, source also not connected. Is there any flux in the core now? Is there any flux in the core? If you don't connect source, is there any flux in the core? No flux. If you don't connect any source, there is no flux in the core, because this is not a permanent magnet, this is electromagnet only. That's why there is no flux here. But when we connect a source to the primary winding, then immediately it will draw a current, a small amount of current it will draw because of no load condition here. Then due to that current, what happened? There are some number of turns in the winding primary side. There are some number of turns N1 and the current IMU is flowing. So which one will develop first? MMF will develop. MMF will develop first. Number of turns N into I product, ampere turn. Due to that MMF, a flux will create. So first mmf will produce, then flux. Now if you apply right hand thumb rule, flux direction is this. A flux is produced in the core. Now the core is said to be magnetized. Flux is developed. There is a flux in the core. This is called magnetized. And the current which magnetizes the transformer core, we call magnetizing current. Okay. So write first one step here. Write one step. Under no load, if the primary is excited from, if the primary is excited from an alternating voltage source, then it is drawing a small amount of current. It is drawing a small amount of current. It is drawing a small amount of current to magnetize the core. To magnetize the core. Hence, it is called as magnetizing current. It is called as magnetizing current. Okay. It is drawing a small current. If it is ideal, what is the current I mean? Zero. So I will tell you the reason also why it is zero. Ideal case, observe here. Ideal. Ideal means what is the permeability we said? Infinite. Mu is infinite. Now according to BH relation, BH, what is B? Mu H. Mu H. H means what? Ampere turn. Ni by L. H is this. H means ampere turn per length. Now observe from this relation, current and mu relation. Current is inversely proportional to permeability always. If permeability is very high, current is very small. Current required is very small. If mu is infinite, then what happens? If mu is infinite, then what is the current required? Zero. So for a infinite permeability core, the magnetizing current required is how much? Zero. But is it possible infinite permeability? No, only finite is possible. So as it is finite means highest permeability we have. That's why a small amount of current it is drawing. That current we call magnetizing current. Okay, now clear all of you up to this. So why we call magnetizing current? Because this current will magnetize the core. That's why we named it is magnetizing current. Okay, now the current I mu, I am considering sinusoidal line. This is what is the current? Sinusoidal. That's why I am taking let I mu equal to Im sin omega t. Sinusoidal. Okay, Im sin omega t. Now, once there is a current, which one will develop first? Once it is flowing, MMF. Therefore, MMF produced. MMF equal to number of turns in primary and current passing I mu. So this is N1 into Im sin omega t. Okay. Now MMF is developed. So once MMF, then flux will produce. What is the flux equation? The flux produced in the core is MMF upon reluctance. So MMF is there, N1 Im sin omega t divided by reluctance. Now, can I write this equation like this? What is the maximum flux in this equation? Maximum. When flux is maximum? If sin omega t is 1. Maximum value of sin is 1. If it is 1, this is the maximum value. Therefore, I am writing this is phi max sin omega t. Phi m sin omega t. Okay. Now, here I will show whatever in the definition we have seen. Current and flux in phase each other. You can observe that is here with equations. We taken current is Im sin omega t. What is the flux we got? Phi m sin omega t, means both are in phase, sin omega t, no displacement, both in phase. That's why flux produced always in phase with current. Okay, next. Now tell me what happens next step. Now you only decide. Now flux is produced. What is the nature of flux? Alternating. Now what it will cause? This flux will produce an EMF in primary and also an EMF in secondary winding. Self-induced EMF, mutual induced EMF. So EMF will induce in the windings. That EMF we need to calculate. Next. Therefore, the EMF induced in the primary. The EMF induced in the primary winding. The EMF induced in the primary winding. This is E1 equal to, according to Faraday's law, completely we write minus N1 d phi by dt. So this is minus N1 d by dt of phi. We have, what is the equation of phi? Just now we written phi is what? Phi m sin omega t. Phi m sin omega t. So I'm writing here. Phi means phi m sin omega t. Now differentiate this. Minus N1 differentiate d by dt of phi m sin omega t. So with respect to t we are doing, so phi m sin omega t will become cos omega t into omega. This is E1. Now I will convert this EMF also in terms of sine equation, that is in terms of sine, because current is in sine function, flux also sine function, EMF also I will convert into sine function. So how can we convert? Observe this. Minus N1 phi m omega cos omega t. How can we write cos omega t in terms of sine? Sine 90 minus omega t. Sine 90 minus omega t. What is sine 90 minus omega t? Cos omega t. Sine 90 minus omega t, nothing but cos omega t. So I will write in place of cos omega t, that is minus N1 phi m omega sine 90 minus omega t. Nothing but cos omega t, same. Okay. Now I will remove this minus also in this. This minus also I will remove by taking the minus into sine of. What is sine of minus theta? Minus sine theta, no? So I will take that like this. So if I take N1 phi m omega, this 90 minus omega t will become omega t minus 90. Sine omega t minus 90. So this is E1, EMF induced in transformer. Primary side it is. In the same way, E2 also you can find minus N2 d phi by dt. That's it. Minus N2 d phi by dt. And now this is EMF induced in the transformer winding. What is the nature of this EMF? So I will write it is as a question. Try to answer. Take the question. The nature of EMF induced in transformer windings. The nature of EMF induced in transformer windings is dash. Transformer windings is dash. So options are instantaneous value, second RMS value, third peak value, fourth average value. The nature of EMF induced in transformer windings. Tell what is the answer? The nature of EMF induced in transformer. Okay, enough. Okay, enough. So some of you giving instantaneous, RMS, peak. Okay, the answer for this question is instantaneous. EMF, nature of EMF induced in winding is instantaneous. That is not RMS, that is not peak. Okay, because if you observe the equation also, this equation is what? Instantaneous it is. Instantaneous means what? This value depends on time. At every instant, different instant, different magnitude of EMF will be there. This is instantaneous because it depends on time. Sine omega t is there in this. This is instantaneous value. Okay, remember this point. Again, it will come. RMS also will come. What is that RMS? You will see now. Okay, this is instantaneous. Now we will convert this equation into RMS equation. Now we will convert this is into RMS. So to convert that, see what is the RMS value? E1 RMS required. What is E1 RMS? RMS value, how can you find? Maximum value by root 2. I think everyone knows this. Maximum value by root 2. RMS value, nothing but maximum value of that equation by root 2. Now, how to find maximum? This is E1. When we get maximum at omega t equal to 180, or if sine function is 1, we get maximum EMF. What is the value of that maximum? This is N1 phi m omega is the maximum EMF if sinusoidal is 1. So therefore, I'm writing here directly E1 maximum is N1 phi m omega. Sine is 1. That is the maximum voltage divided by root 2. Now right here it is N1 phi m. This omega is frequency in radians per second. Now I will convert into hertz. Omega 2 pi f divided by root 2. So this is equal to root 2 N1 phi m into pi into f. Okay, root 2 pi N1 phi m into f. This is the RMS equation. E1 RMS. Now this is I am taking as capital E1. So whenever I write capital E1, that is the RMS voltage. Remember, when I write this capital E1, RMS voltage or RMS equation, that is. So therefore, capital E1 equal to, if you solve this root 2 pi, you will get 4.44 N1 phi m into f. And the same equation we can also rewrite as 4.44 N1 flux. What is the flux in terms of density? B into A. Flux is nothing but B into A. So the same thing I write. Phi m is maximum density into A into F. Now, one small question to you. What is this A here? Area, cross section area of that core where flux is flowing, cross section. Now, we have two areas. If you remember previously, yesterday's class, we have seen. We have net cross section area. We have gross cross section area. Now, which one we have to take here? In EMF equation, what is the cross sectional area involved? Net or gross? Answer this. Net or gross? The area in EMF equation is dash. Yes, right. Good. This is net cross sectional area. AN. So never forget to write AN here, not AG. Never take AG. This is AN because AN is due to iron. AG is what? Iron plus insulating material. But insulating material is not responsible for flux. EMF is due to flux. Flux is in core iron only, not in insulating material. That's why AN we have to take. So this EMF equation. What is this equation? RMS. This is RMS. We have converted the instantaneous EMF into RMS voltage. Okay. So complete all of this equation. See, EMF equation, it is always valid for phase voltages only. Because now we no need to discuss this because some of you asking it is phase or line. This is phase only. If you go to three-phase transformer, same equation, but this equation is valid for phase voltage only, not line voltage. Single phase, no need to discuss. We don't have phase line concept for single phase. Only in three phase it will be. Okay. Next, this is E1 primary side. Now, in the same way, how to find secondary side? Continue the same. Next, EMF induced in secondary winding. EMF induced in secondary winding. Same as it is, you proceed. E2 is minus N2. Same flux is the reason, no? Same flux d phi by dt. Again, proceed same as it is similarly, and finally we get E2. What is the change here? N2, N1 become N2 in this, and remaining all same. Whatever you written here, 4.44 N1, in place of N1, write N2. That's it. Remaining all same. 4.44 BM. BM is maximum flux density, net cross sectional area into F into N2. Only N2 will change. Remaining is same. So this is E2. Okay. Same equation, only N2 will change. Let's write now observations of this EMF equation. From this only numericals we get. Completed up to this, all of you? Yes. Now I want to show one more here. Observe. Current is Im sin omega t. Flux is phi m sin omega t, means both in phase. Now observe. What is the EMF we got? Sin omega t minus 90. Minus 90. Flux is what? Phi m sin omega t. But EMF is what? Sin omega t minus 90. Means EMF lags flux by 90 degrees. No. So in the definition, I said like current and flux in phase, then EMF lags again flux by 90 directly. But the proof is here itself. EMF is lags flux by 90 degrees. Okay. Right. Setting observations of EMF equation. Setting observations of EMF equation. Observations of EMF equations. So let's write the two equations first. E1 equal to RMS equations 4.44 BM AN F N1. Next E2 we got the same equation almost 4.44 BM AN F N2. Okay. E1 E2 primary induced EMF, secondary induced EMF. Now see the first observation. First, so observe the two equations. Observe the two equations. So I'm taking E1 by N1. What is E1 by N1 is EMF per turn it is. EMF divided by total turns will give EMF per turn value. So, and similarly, let us take E2 by N2 also. Now both values same or not? Yes. What is that value? 4.44 BM AN F. So this is called EMF per turn in a transformer. This is EMF per turn. EMF per turn in transformer is same on both primary and secondary. No, E1 by N1 means EMF per turn on primary. E2 by N2 means EMF per turn on secondary. So EMF per turn or voltage per turn in a transformer is same for primary, secondary, or if there is one more tertiary winding or fourth winding, any number of windings, voltage per turn is remains same. So previously I taken directly. Now this is the proof for that also. Okay. EMF per turn in transformer is same. Okay, this is first observation. Next, second observation. See this. Now from the above equation, this one, let's cross multiply this. Now cross multiply, we get E2 by E1 equal to N2 by N1. Cross multiplying the above equation, E2 by E1 equal to N2 by N1. Now what is that N2 by N1? We call K. What is that K? Transformation ratio. N2 by N1 or E2 by E1, anything you can take, that is called transformation ratio. Transformation ratio. And turns ratio is what? Don't confuse in this. Don't confuse in this. Turns ratio means always primary to secondary, it is N1 by N2. N1 by N2. But transformation ratio is secondary to primary, N2 by N1. Okay. Next, third observation. Third observation. Observation important. So if you look the two equations for a long time, also no use. For 1 second also, if you observe, you should observe some important thing in that. So one more observation is the flux density. So before that, I will give one more point. Write this. See, on the nameplate of transformers, nameplate, there is some voltage rating, no? Some 11 kV by 33 kV. And what is this all voltage ratings? RMS voltages they are. On the nameplate of anything, transformers, induction machine, synchronous machine, we have some rating 400 volts if it is induction machine, 400 volts star connected. What is that 400 volts? RMS voltage. Okay. Similarly, on the transformer also we have some voltage rating. What is that voltage rating? That voltage rating is nothing but E1 by E2. So write that point first. The voltage rating, the voltage rating on the nameplate of transformer. The voltage rating on the nameplate of transformer is E1 by E2. So remember, never forget this point. The voltage rating on the nameplate of transformer is E1 by E2. So what is E1? RMS, primary RMS voltage, induced EMF, primary induced EMF, secondary induced EMF. But don't say it is V1 by V2. V1 by V2 is different, but almost same values because of some drops in the windings. But the voltage rating always given on the nameplate is E1 by E2, which is primary RMS voltage of primary, RMS voltage of secondary winding. Okay, it is not V1 by V2. It is not V1 by V2. Always E1 by E2 only. Next, fourth point. Now observe from this equation. Let's take any one equation because both are same, N1 N2 only different. Okay, from this equation I'm taking any one. So let E1 equal to, or E equal to 4.44 Bm An F N. Just N I'm writing. If it is E1, N1 here. If it is E2, N2 here. Okay, anyhow. Now observe this equation. What are the constant in these equations? Always constant values which never change in transformer. Once construction is complete, they never change. What is that? 4.44 anyhow constant. It never change. Flux density, it may change. Area of cross section will change? No. Once construction is complete, you cannot change that. So this is also a constant term. And number of turns inside that, it cannot change. If it is required to change, you have to open and then change. Otherwise, once it is completed construction, you cannot change. But frequency you can change because of source supply, that is whenever frequency is changing, flux density will change and EMF induced in that also change. So therefore, from this relation Bm, so mainly we take flux density here. Bm is proportional to E1 by F. E1 by F. If it is E1, E1 by F. Now the EMF induced in transformer depends on what? Magnitude of flux in the core. The EMF is depends on flux, and the flux produced in the core depends on supply voltage. If voltage is less, current is less, flux also less. If more supply voltage given, current is more, flux also more. So directly it is proportional to V1 by F. Therefore, the flux density of transformer core is proportional to the ratio of supply voltage to frequency. See, never forget this point particularly. It will repeat for every machine. In AC machines like induction machine, synchronous machine, in every machine you will see this word. The flux density proportional to supply voltage to supply frequency. Never forget this. Everywhere it will repeat. Induction machine also, particularly induction motor, we have V1 by F control. One of the speed control method is this. V1 by F control method. Variable voltage, variable frequency control. So these are all from this equation only. From this equation only completely you will deal in induction motors. Important it is. Never forget. Okay. So these are some important observations from EMF equation. Let's see now the phasor diagram of transformer. Phasor diagram. So this is not complete diagram. This is up to the first point. Infinite permeability is the first point. Up to this one phasor diagram. Now to draw this phasor diagram, many people will feel difficulty in this, but you no need to feel difficulty at all to draw this diagram if you follow one sequence. What is that sequence? Simple. See, to the transformer, what you given first? Supply voltage. Okay, then current is flowing, magnetizing current. Then which one is produced? Flux. And then which one is produced? EMF. So if you know this sequence, in the same sequence, we will draw the phasor diagram. Okay. See, first supply voltage. This supply voltage, you can take reference anywhere here. So I am taking, this is the voltage V1 reference. This is V1. This is supply voltage V1 first. So you can draw this line anywhere on this. Like this also you can draw, or like this also you can draw in your book, or like this also you can draw in your book. Anywhere you draw this. Okay. This is our reference V1. Next, what is the next produced? Current, magnetizing current. Now where is that magnetizing current? Lags this voltage by 90 degrees. Vectors direction always anti-clockwise. Now lagging means what? Right side. This is first. Voltage V1 is first. Vectors are rotating like this. Lagging means if it is V1, I1 will be here. Lags by 90 degrees. Current I mu lags the supply voltage by 90 degrees. This is I mu. Okay. First voltage, then current is flowing. That current lags the voltage by 90 degrees. So I mu is taken. Next, which one will produce next? Flux. Where is that flux? 1 second. current lags voltage by 90 degrees. Next, flux is produced. Where is the flux? From the equations also we observed the flux produced is in phase with current. This is phi. Now after flux, EMF induced in windings. Where is that EMF induced? Lags the flux by 90 degrees. Again, EMF lags flux by 90 degrees. So this is E1 and E2 also in phase. E1, E2 in phase, but magnitudes only different. Okay. E1, E2 both in phase. Because what is the reason for both? Flux only. So lags flux by 90 degrees both. Now observe the EMF induced in the windings totally lags by how much angle? It is 180 degrees. The EMF induced lags flux by 180 degrees. Exactly opposition. The EMF will oppose the supply voltage. Okay. So this is the phasor diagram up to first point. This is not complete diagram. Step by step we draw this diagram. Okay. Now let's see some small numericals on this EMF equation. Completed now, this all of you. Completed. Yes. Write the question. Write the question. Two transformers having same EMF per turn, having same EMF per turn and flux densities Two transformers are there, both are having same EMF per turn and flux densities. Next, right. One transformer is operating at 50 hertz with a cross section area of core cross sectional area of core is 0.4 meter square. 0.4 meter square. Calculate the area of other transformer. Area means cross sectional area. Calculate the area of other transformer. Which is operating at 60 hertz. Which is operating at 60 hertz. See, don't look at the size of the questions here, particularly for machines. Maybe whatever the size, first you need to read the question with patience. Nothing is there in the questions. What is the answer? Yes, Surojit, right. Yes, good. Achita, right. Yes, the answer is 0.33 meters square. 0.33 meters square. Good. Yes, right. Enough. So here there are two transformers. Let transformer A, transformer B. What is given? Both having same EMF per turn. EMF per turn, E by N of this, E by N of this. Both are having same EMF per turn and flux density. What is EMF per turn equation? E by N equation. Just now we written 4.44 Bm AN F. 4.44 Bm AN F. Also given that both having same EMF per turn and flux densities, means Bm also cancel. 4.44 anyhow cancel. Same EMF per turn. That's why both equated. Now, one transformer operating at 50 hertz. Indian transformer, US transformer. US transformer frequency is what? 60 hertz. No. Now, one transformer 50 hertz and its area is 0.4. So 0.4 into 50. Next, other transformer frequency 60 hertz. Now we need to find what is the area of that 60 hertz, which is operating at 60 hertz. Now, what is the area of other transformer? AN equal to, if you calculate this 0.4 into 50 by 60, you will get 0.33 meters per. So what is your understanding from this? What is the understanding from this question? Suppose if you get any question, there is Indian transformer, US transformer, both having same EMF per turn and same flux densities. Then which transformer is small in size? US transformer. Because what is the area we got? Only 0.33 meters square. So US transformer size is small compared to Indian transformer, which is operating at 50 hertz. Okay, so remember this. Next, one more question. See this. See the question. A 250 kVA 11 kV by 400 volt 50 hertz single phase transformer has 80 turns on secondary. What is the maximum value of flux? Direct substitution. So where turns is given? First of all, what is the voltage rating given here? This is E1 by E2. Okay. Always the voltage rating given is E1 by E2 only. E1 is 11,000 volts, E2 is 400 volts. And 80 turns on secondary. So N2 is there, 80 turns. Now we need to find the maximum value of flux, phi m we need to calculate. So what is the EMF equation? So as there is N2, we have to use E2, 4.44 Bm, not Bm, because directly phi m, in place of that B into A, direct phi m you have to take. Phi m is BA. So based on the question, we need to take that. So phi m is here directly taken into N2 into F, direct substitution. E2 is there, 400 volts, 4.44. We need to calculate phi m. N2 is there, 80, frequency 50. Calculate phi m from this. Phi m, how much? How much it is? Calculation. Take care of these points. Yes, this is 0. What? Yes, right. 0.0225 in milliwebers. 22.5 milliwebers it is. So in milliwebers options are given. So convert it is into milliwebers. 22.5 milliwebers. Okay, next question. Next, last question. Do this. Read the question first. Read the question. 400 by 200 volt, 50 hertz transformer operates at a flux density of 1.2 Tesla when energized from its high voltage side. So read this carefully. For this transformer, linear dimensions of core are double. Linear dimensions means length and breadth of the core is double, while the number of turns are half on both HV and LV side. If this transformer now connected to 800 volt 50 hertz on HV side, if it is now connected to 800 volt 50 hertz on HV side, then flux density is dash. Direct based on EMF equation, you need to solve this. Simple. So initially, where it is energized, see 1.2 Tesla when energized from its high voltage side. With respect to high voltage side only, we are talking. High voltage side, what is the voltage initially? 400 volts. So E1 equal to 4.44 Bm AN F N1. This is the equation, EMF equation with respect to primary. Because why we take an E1? Because they said with respect to HV side, primary side, that is here. What is that HV voltage? 400. Initially 400 volts applied. At that time, what is the flux density? 1.2 Tesla. And they, at that time, there is some area here that is not mentioned. There is some area, frequency 50 only, and there is some number of turns. So let given is Bm1 equal to 1.2 Tesla. N1 is not given, but what is given? The number of turns is half on both sides. Whatever is there previous, now it is half. So let us take N1 equal to N. And area AN1 equal to, let us assume A. What is area of core? Length into breadth. Length into breadth. Some length is there, some breadth is there. Linear dimension. Now the question here is, see, for this transformer, linear dimensions of core are double. Means new area we get. No? What is new area? Linear dimensions are double. Length become 2L, breadth become 2B. Now what is this? 4LB. LB is nothing but A. So this is 4A. So new area we got. New area we got. If this transformer now connected to 800 volts, now voltage is 800 and new flux density we need to calculate, and number of turns also mentioned half. Number of turns are half. Okay. Now from this equation, in two cases I will write. First case is 400 volts applied. Now second case is 800 volts is applied. So E21, E12, primary side only, second case, divided by E11 equal to 4.44 Bm2 AN2 Fn2 divided by 4.44 Bm1 AN1 Fn1. Now all values are there here. We directly substitute. E12 means how much? 800. How much voltage applied now? Given now 800 volts. That's why. And previously how much voltage? 400 is applied. Now substitute all the values directly. Calculate from this equation what is the new flux density. Bm2 is how much? All values are given. Calculate Bm2. How much? Yes. Answer is 1.2 Tesla. Means same you will get. What is there previously? 1.2 Tesla only there. Now also 1.2 Tesla. After changing this linear dimensions and number of turns half, you will get same flux density again. Okay. So question is little confused. You try to understand only on primary side. Previously 400 volts applied. Now 800 volts applied. And there is some changes in linear dimensions and number of turns. That is we substituted. And we got the new flux density same as previous. 1.2 Tesla. Okay. So with this, we stop today here, and some more numericals we solve tomorrow on the same EMF equation. Okay. So, Jayasree.
Sir, good evening, sir.
Yeah, good evening. Tell
Yes,
me.
sir. Good evening, sir.
Tell me.
Sir, in 68F, sir.
50,
68, sir.
68.
Yes, sir.
Hmm.
Sir, here also you have discussed about the uh, direct flux linking with the secondary, sir.
Uh,
And before also by increasing the width of the second
yes, yes.
core,
Uh,
you said that
uh,
is not desirable in that case.
uh,
But here you are telling that it is desirable. Like
no, your doubt is not.
how
Ask one more
how it
time
is,
question.
sir. I itself got confused, sir. How both are different, sir?
Voice little breaking.
Sir, while
Hmm.
reducing the width, you said
Yes. Hmm.
the direct flux is linking with the secondary, so it is not desirable. So we don't reduce the width like that.
No,
You
no,
said,
that
sir.
is that height and width is completely different. No, this is placement of winding. So before placing winding, with respect to core only we talk there. In the
Okay, sir.
transformer core construction only we talk no, about height and width. If you change the height and width of the core, with respect to that, some leakage fluxes may change. But what is here with respect to winding placement? We are not talking about dimensions of core here. They are fixed. With respect to placement of winding, how the leakage flux will vary. Okay,
Okay,
don't relate both.
okay, sir. In 69F, sir.
Uh,
Sir, here LV is thin while stepping down, sir. Why can't we take like in the last problem also HP side they have taken as primary, sir.
Anything, anywhere we can take as primary secondary. No, the primary secondary may be any winding. That depends on our
Okay, sir.
requirement. Suppose I have a load which requires low voltage now, then I will
Yes,
give
sir.
supply to high voltage side.
Okay, sir. In that case, but you said LV side is always we are having thick wires, and HV side is always we
Yes,
are
yes,
taking
yes.
thin wires.
Thin wire. Yes, yes.
Sir, uh, but I was taught like primary will have less number of turns than
No, no,
secondary.
not like that. Not like that.
How?
Primary mean I said in the first class also. Primary winding is which winding? Wherever you connect source.
Yes,
That
sir.
may be LV winding. That may be HV winding.
Yes, sir. But
Okay. Mm.
that case is wrong, no, sir. Primary will have lesser number of turns than secondary. That
Oh,
is wrong.
no, no, that is wrong. That is wrong.
Yes, sir.
Primary means anything. That may be LV or HV. Anything.
Okay, sir. In this case,
Mm.
also, how you said repulsive force, sir, that I cannot understand. So, can you explain once?
Because here two windings are placed adjacent, no, LV and HV.
Yes,
And
sir.
when two windings are on same limb, they should carry current in opposite direction. One winding, one direction current, other winding, other direction current. At a time, both are flowing. Then two current carrying conductors in
Then it
opposite
should be
direction.
a attractive only, no, sir.
No, see the statements previously. If two conductors carry current in opposite direction, there is a repulsive force. Same direction,
Yes.
attractive force.
Okay.
Okay.
Yes, sir. Okay.
Okay.
Thank you.
Jitendra.
Hello.
Tell me, Jitendra.
Sir, in the phasor diagram that you have drawn today for
Uh,
the ideal transformer,
uh,
sir, there V1 is opposite to E1 and E2,
yes.
a 180-degree phase difference. So, sir,
Yes, yes.
in the circuit diagram of that transformer,
Uh,
sir, what does that mean? V1 and D1 are opposing each other by 180 degrees. So, does that mean that there is
uh,
zero voltage across any 2 points?
Zero voltage across.
Any 2 points on the primary side, because V1 and D1 are opposing completely. So they will,
Opposing means this is V1 is not exactly equal to E1 na, in magnitude. See, actually V1 EMF induced is E1 and there is some drop in the winding impedance drop I1 Z1.
sir, for ideal I'm asking.
Ideal both are same. V1 equal to E1.
So sir, does that mean between
Hmm.
any 2 points there is no voltage difference?
Yes, 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 right.
So sir, if there is
Ideal case,
no,
that's why current zero, no? Ideal case current zero.
but current is there, no sir, I mu.
Ideal current zero only, no, I said. Practically there is a small current.
No sir, in this the case that you discussed today, in that
Uh,
also we have taken no I mu, and still V1 is equal to E1.
where in the equations?
In the circuit diagram that you've drawn 2 slides back.
Where it is?
For this case only.
This one?
Yes, sir, this case. The circuit diagram is, I think, in 1 slide back.
Where it is? Side number.
This one only, sir. So, sir, here also V1 is equal to E1, and we have taken I mu also
Uh,
in the circuit.
this is not ideal, no. This is a finite permeability we taken. This is practical case, no.
So, in this case only, sir, V1 is equal to E1, no?
No, no, no. Practically not V1. V1 is not exactly equal to E1. There will be slight difference. Otherwise, current should be zero, no.
Okay, so here we are not taking V1 equal to
Hmm.
E1.
No, no. This is practical case. Ideal case, whatever you said is right.
Okay, sir. That's what I wanted to ask. Thank you, sir.
Okay. Okay. So, Pranjali,
Hello, sir.
tell me.
Slide number 69. Placement of winding on the core.
Hmm. Hmm.
Sir, in that when we place HV winding first, so there
Ah,
we have taken 3 kV for HV insulation and 1.5
yes.
for what?
LV insulation. Because between HV and LV, one more insulation you have to place, no.
Then
Potential
sir, in when we
difference.
have taken
3
LV
kV.
first,
Huh?
sir, then when we have taken LV first, then why didn't we take 1.5 and then 3 kV? Because 1.5 is for LV insulation and then we should take 3
LV, see,
kV for.
LV insulation means not directly that LV voltage. Every time you have to place where is insulating material between two voltage levels. No,
Hmm.
that's why
Yes.
potential difference you have to take every time. Not directly that HV voltage, whatever is there.
Okay, difference between the two windings.
Uh,
Okay, okay.
two levels, two levels.
Okay, okay. Thank you, sir. Understood.
Okay. So Vaishnavi,
Sir, in 70F, sir.
uh,
Sir, this one not, sir. In advantages of placing LV winding nearer to the core.
okay.
In that fourth point, when the windings and core are nearer, then there will be less length, no, sir. Length between
Leakage
them.
flux is less. Less distance between
Less
core and
distance
windings.
means less reluctance, then more flux will generate, no, sir. Then leakage flux also will be more, no, sir. How it can reduce?
You are you don't consider like leakage flux means what? It passing in the air. Okay, whatever the flux in the core produced, leakage flux means it is passing in the air but not in the core. So when distance between core and winding increase, as air gap is coming more, no, in between winding and core, then most of the flux lines will get leakage. So most of the lines will not enter into the core. They will be in the air itself. So that is we taken as more leakage flux. If distance
Leakage
is more.
flux means the flux with only one winding, no, sir.
Only
That
one
means-
winding, yes.
Then you said here again the flux in the air like that, no, sir.
You are confusing between leakage flux and main flux. You are considering
Yes.
that when distance is near, reluctance is less, flux produced is more.
Yes, sir. I am considering.
Yes, the flux produced is more means that flux is in the core now. Then leakage
Yes,
is
sir.
less, no?
Sir,
Okay.
again, okay.
Hmm.
Sir, in magnetizing current explanation, you said in 81 F, sir, 81 F.
81. Oh,
Sir, here, what is the meaning of magnetizing the core means, sir?
the flux created na, in the core. Before giving supply, is there any flux in the core?
No, sir.
No flux. Then when we give supply, flux is generated, no?
Sir,
Now core is said to be magnetized.
From current, how flux will produce, sir?
Current is flowing, no? Once voltage source is given, it is drawing a current, small current.
Yes, sir.
Due to that flux produced. That as it is magnetized, flux increasing in flux we call magnetizing. Decrease in flux we call demagnetizing. Now it is magnetizes, flux produced. Previously zero, now developed. That's why we call the corresponding current magnetizing current.
I am asking, is there any experiment to know that from current how flux is produced, sir?
You have to go to directly just like magnet it is. So excite any any iron bar with a supply, then it is acting as a magnet means flux is there na, in that small
Yes.
experiment. Then you can understand.
Sir,
Okay.
sir, again, one more doubt, sir. We are using in shell type sandwich winding process, no, sir. Why
Yes.
can't we use this process in core type, sir?
So in core type, there is no need now because there still to reduce leakage flux we are going. Already in core type, leakage flux is more. For that, we are going to reduce little interlink between LV winding and HV winding. So there is no chance to place like sandwich type procedure in shell type, core type transformer. There is no chance. No, only one limb is there. How can you place one after other like a layers? So that is not suitable for that. Okay. Amit Vikram.
Sir, why do we need to place insulation on the core before placing the winding? Can't we directly put it? Why is the what is the reason?
No. Because if you directly place the copper wire may get directly contact with the iron body, no? Then iron body will also behave like a conductor. There directly short circuit will takes place no, between the both. Just like in motors also, in every slot we place insulating material. What is the need of placing insulating material? Directly can we place winding in that? No? Winding itself having insulation on that. Suppose if you take any copper wire, no, there will be oxide paint coating will be there, insulating material on that. Directly you can place, but that is very small. Once it damage, it may get directly contact with iron body, short circuit will take place. Just like in your home also, ceiling fans will burn, winding will burn. Same reason, insulation damage, both gets short circuit.
Thank you, sir. Got it, sir.
Kumar.
Hello, sir.
Tell me.
Sir, if we give what the signal to primary, that signal will appear in secondary, sir. In first class, you said, no?
Not understand. What is ask again?
Sir, if we give square wave, the secondary also we got.
Yes. Square wave. Yes.
Okay. If we give the signal like.
Whatever you given, same will come outside.
Hello.
Tell me.
Sir. Hello.
Kumar, tell me.
Sir, if we give the signal u of t minus u of t minus 100,
Uh,
then the output signal also same, sir.
U of t,
Minus u of t minus 100.
t minus 1.
T
So
minus
maybe it
100,
could
sir,
be
not 1.
t minus
Means 100, sir, 100.
100. Okay, then 0, I think.
Why, sir? Actually, the statement is like,
This is like DC sub DC, no? It is constant voltage.
yes, sir.
Constant
Okay.
for long time. If you apply DC voltage for a DC voltage for a long time to transformer winding, what happened? First winding will burn. So you should never apply this type of signals to transformer.
Hello, sir.
You should not apply this type to transformer, no? DC supply.
Yes, sir, but okay, sir. Actually, if we apply DC, there is no change in flux, so there is no
EMF 0.
EMF induced in the secondary. But
Yes.
as per the we written in the equations like that, sir. Phi is is that
No. That
E1
is
is equal
valid
to LDI by
only.
dt.
Uh,
So there we got I is equal to 1 by L integration of U voltage.
okay.
So
Okay.
if you apply supply voltage like U of t, we got ramp, sir.
Yes, but you
Again,
are
if we
see with respect to signal you will get that. But what is transformer? You should never apply a constant voltage for long time to transformer like DC supply. So T minus 100 means plus 100 seconds. Suppose you applied means definitely windings will burn. You should never apply this type of signals. Okay.
yes, sir.
Mathematically you will
Okay.
get some waveforms there, but that is wrong.
Mathematical so condition it will wrong.
Yes.
Okay, sir.
So Akshaya. Hello. Srikant Sahu. Yeah, tell me.
Hello, sir. In 88F. Can you please explain this relation again, sir?
Which one? Fourth one?
Fourth one, sir.
From the equation, which are constant values always once construction of transformer is completed, no? Which are constant in this? 4.44 is a constant value. Area of core will never change. Number of turns also will never change. And remaining 3 are the variables. Why? If you change the supply voltage or supply frequency, then EMF will change, frequency anyhow you are changing, and flux density mainly depends on this voltage and frequency ratio from this. E by F it is. E by F. So I taken E1 by F because this is primary side E1 by F. Now this E1 depends on supply voltage only, no?
Yes.
So E1 proportional to V1. That's why I taken V1 by F ratio. So flux density always proportional to V1 by F ratio. So tomorrow we will see some questions on this equation. Okay.
Okay, sir. Okay, sir. Thank you.
Okay. Next, Sagarika.
It's sir in second sem, sir. At starting of class you said no, second sem. Second sem, sir. Today's
Today. Page number
I don't know. Like
this one.
ERS one, sir. ERS and ES, sir.
Okay, you are saying they are asking ERS here, right?
Not this, sir. Here we are finding secondary EMF, no, sir. By formula, E2 is equals to MD5 by dt, you know.
Yes.
Then in d5 by dt, like, I mean, this is also correctly like what will be the difference, sir? MD by dt.
See. N or M?
sir.
N or M? Mutual
M,
inductance or N?
mutual
Number of
inductance.
turns. E2 is M di by dt, no, not d phi by dt. When there is mutual inductance and current, then we use this equation, because
Means
here
flux. Okay.
flux is given, no, that's why we taken N d phi by dt.
Okay, sir. Sir, and this normal dot, like if we provide insulation between primary and secondary, how flux will travel, sir, through air?
Flux will not travel through insulating material. How the flux generally see? Flux will travel in a coil like this. If it is a coil, if you excited with a source, na, here V1F, then current is flowing, and how flux will produce? Like a closed loops, now like this. If there is insulating material also, flux is not going like this. It is taking path like this. Okay.
Okay. So
who is this?
79 F, sir. I will ask 80, sir. Sorry. Okay, sir. Finish. I mean, I got it.
Sir?
Jayasri.
Sir, yes, sir. One general doubt, sir. Sir, in 68 F also, there, I mean, in placement of winding on core, there also the direct flux is linking with HV, no, sir? Sir, how is that alone taking into effect, and is that okay to have direct flux on the HV side, sir?
Direct also okay. What is our main aim in transformer? Whatever flux produced in primary, that should reach to secondary. For that, we are providing core.
Yes.
Okay.
Sir.
If there is no core, how it will go? Through air, it has to go. But
yes.
Air is offering very high reluctance. No. If it is going through air, it's still very, very best for us. But it won't go, no. Because it will provide low reluctance core compared to air.
Yes.
Maybe some flux lines will reach through air. That is advantage for us.
But here the reluctance is less, since the LV and HV are the length between those two is less, no, sir?
Yes.
Oh, thank you.
Mr. Shiva.
Hello, sir. Good evening, sir.
Yeah, tell me. Good evening.
Sir, in 59F, sir.
Okay.
Sir, here we are calculating the ESR value based on the actual dot portion only, right, sir?
Actual dot is at yes, but they given wrong. They given dot is at R, no. So whatever you calculated here, this is better you consider ESR it is. Okay, then your doubts will be clear. This is ESR. According to our dot, this is ESR. But what they are asking? ERS. This is ESR. If it is ESR, these values are correct, whatever you calculated. But what is they are asking? ERS. That's why reverse we take.
Okay, sir. Here the actual dot is in the negative polarity, so we are considering
yes,
the
yes, opposite.
sign.
Yes.
Okay, sir. Okay, so that's it.
Okay.
And
Pratyush.
Hello, sir. Sir, I have doubt regarding yesterday class, sir.
Tell me.
Sir, you said by laminating we can reduce eddy current, no, sir, eddy current losses. Also, complete 100% core staggering is not possible, no, sir, practically.
Yes, yes.
Sir, then there will be tiny air gaps. Due to those tiny air gaps, reluctance will increase, no, sir. Is not considering the effect, sir?
reluctance will increase. That's why current drawn first drawback I said there due to that poor core staggering. First drawback is what? Thin air gap which offers high reluctance. Because of that, the current drawn by transformer little increases.
Yes, sir. Means before laminating, less reluctance, means after laminating somewhat there will be increase, no sir. That is not major
Yes,
or
yes.
not.
Because majorly why we are laminating, not for the purpose of reluctance, mainly for the purpose of reducing eddy current loss, heat in the body. That is important for us. Maybe little reluctance is increasing according to the gaps. So due to that little current increase, but more advantage we are getting. Loss is reducing, no?
Okay, sir. Sir, another doubt, sir.
Practically also, if you conduct this small experiment, you can find so much heat in the iron, so much heat. So
Okay,
maybe people don't know, practically you can understand just for 10 to 20 second also, if you give some supply to any iron structure, the heat produced is very, very high.
Okay, sir.
Okay.
Sir. Hello, sir.
Yep. Who is this?
Sir, Prithvish, sir.
Tell me.
Sir, when moisture enters into transformer, what will happen? Sir? What effect comes?
Because of moisture, the dielectric strength of oil will reduce.
Okay, sir.
Oil is acting as insulating material, no?
Yes,
Suppose
sir.
if some impurity is added to any original liquid, what happens? Its property gets damaged, no?
Okay, sir.
Moisture will damage the dielectric strength property of oil, transformer oils.
Okay, sir.
Not only that, if moisture enter into the iron body, it may get rust also.
Okay, sir. Sir,
okay.
Sir, in this sum, we can use this formula, sir. E2 is equal to, if they have given M, sir, M into di by dt.
Yes, when there is current signal, you can use with M.
Or L2 into di by dt, sir.
N in d5 by dt or M di by dt. Anyone.
Okay, sir. Sir, last doubt, sir. Sir, you should shell type is used for low voltage application, no, sir.
Yes.
Because sir, that reason once you explain, sir.
One reason is we can accommodate only less number of turns because less area inside we are placing. After placing some turns, gap will fill. Then where you can place more than that. That is one reason. And other reason is insulation problem. More insulation required. More insulation means generally when voltage increases, insulation also increases. So high voltages, very high insulation required. When insulation increase, fast increase. So for that reason, low voltage only it is best.
Sir, but at the middle of area, the width of the turn will be more, no, sir. Means length of the copper required will be more, no, sir.
Anyhow, shell type means we need to place there only, no, because two winding carrying current both will produce so much flux, so much area required. Otherwise, if you place in the thin limb, easily it will saturate. Okay.
Okay, sir. Thank you, sir.
Ayyappan.
Sir, 64th page, sir. 64.
Tell.
The window spectre, how to reduce the leakage of flux, and another one time to explain.
Leakage flux means it is flowing in air. If you increase height, no. Okay, what is the length it is passing? More length it is passing. Length increase, no. Observe, first one is this much length. But second one, when height increases, this much length it is crossing. So whenever length increases, reluctance offered to flux increases, leakage flux. Then leakage flux will reduce.
Length of the leakage flux instead to reduce.
Yes, yes.
Okay, sir. Okay, sir. Another one doubt, the EMF equation, sir. The sin omega t minus 90 degrees, how to eliminate, sir?
How to?
Eliminating, sir. Sin omega t minus 90 degree.
We are not eliminating. We are not eliminating because here we got cos omega t. Okay, in place of this cos omega t, we are writing sin 90 minus omega t because both are same, no?
Yes, sir.
Sin 90 minus theta, cos theta.
Yes, sir.
That already there is minus outside here.
Yes, sir.
This minus we taken inside of sign, or sign of minus theta we applied, minus sin theta, minus minus plus, then omega.
Okay, sir. Okay, sir, we finish.
Hello, sir.
Vinita.
Yes, sir. In the same doubt, sir. In 64F.
Which doubt?
Sir, how leakage flux decreases by increasing the height, sir? I'm not getting it.
Actually, flux is what MMF by reluctance, no?
Yes, sir.
Means flux is inversely proportional to reluctance. So flux reluctance is proportional to air gap.
Yes, sir.
Air gap. If air gap is more, if length of air gap is more, then automatically magnitude of flux will reduce in that path.
Yes, sir. But we are increasing the height, no, sir. Then air gap also increases. Okay, sir. Got
When
it.
air
Sir.
gap increase, that magnitude of flux decreases, leakage.
Yes,
Whatever
sir.
flux
Then
coming in that path, that will decrease.
okay, sir. Got it. Thank you, sir.
Mr. Dhanvi.
Sir, my doubt is in advantages of placing LV winding near to the second point, sir. Sir, in this point, you said that since the LV winding is near to the core, the cost of the transformer reduces because diameter is less. Sir, but if the diameter is less, for the HV winding, the diameter is more, and there are more number of cores. So whatever cost is gained in the for the LV winding, the same amount will be extra will be put to the HV winding, sir.
But
The diameter is
over
more,
that,
more number of turns, more copper will be required.
okay, maybe you are thinking that after placing LV, insulation is placed and overall diameter for HV winding is increased, then it is requiring more copper wire for that. But you should not think only that HV. If you place HV winding first, then place more turns HV winding, and over that again insulation, over that again LV winding. Then overall you have to consider overall things, not only one case of winding. Okay. Totally, if you take, definitely it will reduce. Okay, I'm closing for today. Tomorrow we meet at same time.
Hello, sir. Sir, last, sir, one doubt, sir.
Who is this?
Sir, Pratyush. Sir, you said for connecting the transformers in parallelly, we should know the dot polarity, no, sir?
Yes.
Sir, how in practical world they'll connect sir parallelly? They outside.
Have some patience, no, up to that.
Okay.
Okay. So there we see clearly, because now I cannot clarify in one statement, that is. Okay.
Sir, okay, sir. Last another doubt, sir. So you said noise will come due to phenomena of magnetic restriction, no, sir?
Restriction. Yes.
Sir, but in other mission like synchronous, due to the harmonics in flux, there will be some vibration, no, sir?
Yes.
So that is also
that is also humming noise one.
Okay, so
but you cannot listen that, because their rotating noise will come more, no?
Yes, sir.
That's fine.
Okay, sir. Thank you.
Okay. Good night.
Okay.